And then he called me on the phone and he said, am I reading this paper right? Are you saying that these fossils were in the meteorites when they entered the Earth's atmosphere? And I said, yes. He said, you're saying this is extraterrestrial life? And I said, yes.
Welcome to the continuing series of the award-winning Mars documentary titled Blue Planet Red. There's more to Mars than you might think. Water, life, pyramids, UFOs, cataclysm. Watch the film online at blueplaneted.net. Today we're speaking with Richard Hoover, a former research professor, astrophysicist, and astrobiologist at NASA's Marshall Space Flight Center from 1966 to 2012. Originally recruited to Wernher von Braun's team to work on optics for the Saturn V rocket program, he ultimately became the first director of the Astrobiology Laboratory at Marshall in the wake of NASA's discovery of possible microfossils in the Allan Hills meteorite that fell to Earth in 1984. He has 11 patents, and in 1992, NASA selected him as their Inventor of the Year. He led their astrobiology research department on numerous expeditions to Siberia, Austrian Alps, Canada, Iceland, Alaska, and Antarctica, searching for and ultimately reanimating dormant microbes previously frozen for millions of years. Previously, and in no uncertain terms, Professor Hoover briefly explained his microfossil discoveries to journalist Lee Spiegel.
I am absolutely convinced that life is not restricted to the planet Earth because I have found the remains of life forms that are absolutely, conclusively extraterrestrial. When I take those meteorites and I break them under very precise conditions in flame-sterilized pans with totally propane torch flame-sterilized tools and fracture the meteorite and put it on an electron microscopy stub with the freshly fractured surface up and then put it into the field emission scanning electron microscope, I find the obvious and recognizable remains of biological entities.
He also responded to his critics.
So why then do skeptics or debunkers of such claims say that what you're looking at really are microorganisms as a result of contamination when the meteorites would hit the ground or hit the snow, and then somehow these microorganisms found their way onto or into the meteorite?
The only explanation is that they either did not read the papers I have published, or if they did read them, they simply did not understand them.
Now retired, he volunteers at the U.S. Space and Rocket Center in Huntsville, Alabama. Today, we'll discuss in exquisite detail the history of discovering microfossils in meteorites from 1961 to 2024.
When we talk about microfossils in meteorites, to someone who has no concept whatsoever what that means, how would you explain that to them?
Well, very simply, a fossil is the remains of something that at one point in time was living. Typically, they're ancient. They don't have to be. Diatoms, in fact, are almost what you might call instant fossils because as soon as they die, their shells are just about the same as they're going to be after millions of years. So they don't undergo many, many changes, although the organic matter disappears fairly rapidly. A fossil is the ancient remains or preserved remains of a once living organism. A microfossil is the ancient or preserved remains of a once living microscopic animal or plant.
In a rock?
In a rock.
Okay.
Well, not necessarily. They can sometimes be in ice. You can have microfossils that are preserved in all manner of sediments, but many of them are found in rocks.
Okay, so for these ones that are found in the rocks that fall from the sky, we call them meteorites, okay? So for the people listening who have never heard of this or who don't believe that these rocks that fall from the sky have these little tiny fossilized critters in them, they don't believe it.
Well, science is not about belief. Science is about fact and observation and data. So, in point of fact, the people that have looked at the proper meteorites with scanning electron microscopes and have the ability to recognize biological entities do realize it's correct. The point is, first of all, you have to have sufficient knowledge to know what microorganisms look like. In fact, there are many microorganisms that are not recognizable to people that have never studied bacteria or rotifers or cyanobacteria or any of these kinds of life forms. If you have never looked at microfossils, you really would not have necessarily a realization that that's what you're looking at. Now, if you look at a fossil diatom, just about everybody that looks at a diatom would say, yeah, I think that was alive at one point in time. But bacteria and things like that, many times they're very, very difficult to recognize. And some of these smaller, for example, when I'm studying meteorites, I ignore the conchoidal forms or spherical forms because there are lots of ways that spheres are made without anything to do with biology. All you got to do is go outside when it's raining, and you're seeing lots of spheres falling out of the sky. Have nothing to do with that they were once previously living organisms. They have a great deal to do with life because water is essential for life. But you take an asteroid and you slam it into the surface of the moon and you melt and vaporize moon rocks. And when these melted chunks of moon rock go up above the surface of the moon and fly to a different place, as they're traveling in their trajectory, they frequently solidify. And when they solidify as little tiny spheres, and sometimes two of those liquid spheres of rock will collide together, and you get a double sphere. Well, if you're a microbiologist and you look at that, you would say, that looks like a conchoidal bacteria, or that looks like a diplococcus, which is two spherical bacteria that are joined together. But has nothing to do with biology. It's melted rock, and they form spheres because of surface tension. So it's a purely physical phenomenon. So if you're dealing with microfossils in meteorites, you really want more morphological detail than simply spherical structures. You really want to see things that can be recognized as undeniably biological. One of the things that constitutes that, for example, is chains of cells, or cells within sheaths. Cyanobacteria, for example, are algae. Well, they're actually truly bacteria, but for centuries, they were considered the blue-green algae. And that's because if you go out to a pond and you see some blue-green slime floating on the surface of the pond, you would say, oh, there's blue-green algae. And for a long period of time, those were considered to be plants. But we now know that they are not plants. Plants are eukaryotic organisms. They're, of course, eukaryotes include the plants, the mammals, the animals, the rotifers, the paramecia, the amoeba. Those are all eukaryotes. The bacteria are called prokaryotes. The prokaryotes are considerably simpler in many respects than the eukaryotes, but they also have amazing complexity as well. So the point is, if you look at prokaryotes, the reason that cyanobacteria are recognizable is because many of them form filaments in which you have many, many cells together, and they envelop themselves in what's called a sheath. That's kind of like if you have a bunch of BBs in a soda straw. The BBs are the cells, and the soda straw is the sheath on the outside that contains them in one place. Now, there are many cyanobacteria in which you have all of them in a single soda straw type structure. There are others where you have many of these soda straw type filaments wrapped within a big envelope. And that's the different kinds. The ones that are only a single group are called the monoceroid. The multiple group or the multiceroid cyanobacteria. Sometimes they build special cells that are used for nitrogen fixation, and those are recognizable. Sometimes they have special cells at the end of the filament. Sometimes the filament tapers. So the basic point is, in order to recognize these, it's really a good idea to study them in living state and in preserved state. It's really a good idea to learn these aspects of botany and bacteriology in order to recognize what you're looking for.
Okay, so do you think most astrobiologists today, okay, in their, let's just say 20s and 30s, do you think they know all that?
Well, I know for a fact that a vast majority of them probably don't, because you can be an astrobiologist if you're interested in the formation of planets. You can be an astrobiologist that works on galaxies and galaxy clusters and so forth. Astrobiologists do many, many different things.
Well, who are the ones studying
the astrobiologists that
microfossils?
study microorganisms know every bit of this. They absolutely know every bit of it.
Are they called, do you call them astrobiologists?
Of course.
Do they call themselves astrobiologists?
Of course. Well, I mean, many do. And many astrobiologists have extreme knowledge of paleontology, of micropaleontology, and of bacteriology. And the astrobiologists that know microbiology, when they look at the fossils in the meteorites, they will say, yes, they are biological, but many of them will say, but they look so much like Earth life, they've got to be terrestrial contaminant.
All right, we'll get to contamination. Now,
Okay.
for those people, okay, even who consider themselves to be astrobiologists, who take a look at the photos you've produced and say, well, you know what? You can't say that this is a microfossil based on morphology alone.
That's nonsense. Absolute, total nonsense. If I told you to go get my car, which was out in the parking lot, and told you it was an XF Jaguar, and you came back with a VW Beetle, I would say, how come you couldn't recognize my car? Well, I can't tell anything about automobiles by morphology alone. Well, the only thing wrong with you is you don't have much sense.
They don't have the proper training to identify something
Well,
like that, right?
no, I think all of the people who know microbiology have the proper training to identify it. And in fact, I have never had anyone try to argue with me that when I gave a lecture at the Institute of Microbiology of the Russian Academy of Sciences. It was chaired by academician Zavarzin, who's one of the world's leading authorities. Well, unfortunately, Georgy Zavarzin is dead now. But academician Zavarzin wrote the book that microbiology students of Russia studied in the graduate school, one of the world's leading authorities on cyanobacteria. And I showed these images, and it was a room full of people from the Institute of Microbiology. So they knew microbiology. And Zavarzin, when I finished, says these remains are remains of cyanobacteria. I'd like anyone who disputes that to please speak up. And we stood there for about 2 minutes. And then he turned to me and he said, Richard, the silence is deafening. And the reason was everybody in that audience knew if anybody should speak up, it should be academician Zavarzin, because he knew cyanobacteria. And of course, many of them worked with cyanobacteria also, and they knew it, like Galina Ushatinskaya and many of the others.
Okay, what year was this about?
Wow, that was a 1997 lecture.
Okay, that was a while ago. All right.
Yeah.
Now, which is surprising, I think, because this isn't new. This study, these photographs, this data that we're collecting. But let's just, okay, let's play along here, all right?
Okay.
Say, for instance, all right, you find one of these not so recognizable formations, all right? It takes a really trained eye to discern the difference between part of the rock and maybe something that's perhaps biological. So if we're not using morphology at all, what are some of the other qualities that you're looking for to identify that, yes, this is biological and it wasn't contaminated? What are some of the other qualities besides morphology?
Okay. Well, one of the beautiful things about the scanning electron microscopes is, and that's one of the arguments people make, oh, well, all you're doing is looking at morphology. Well, they're completely wrong, because in order to recognize biological remains or biology, you don't look just at the shape of something. Morphology is much more detailed than just shape, as though this is a rectangle or this is a triangle. But in addition to that, to the detailed morphological structures that you can see, in fact, you're a general shape, but I can see you've got a head, a face, hands and arms, and that identifies you as a human being, most probably, unless you could be a chimpanzee and have those same features. But if I looked, I could probably tell the difference. And just about any person who knows anything at all would be able to tell the difference between a human and a chimpanzee, or a dog and a cat. But you can do that on morphology alone.
So, but generally...
But
okay.
Back to the electron microscope.
Sure.
We not only look at morphology, we look at, and by that I mean structural details, but we look at size. Size matters. Size is very important. We not only look at size, because size matters, but we look at chemical composition. We have energy dispersive X-ray spectroscopy that allows us...
One more time.
Energy dispersive X-ray spectroscopy. What happens is the electron beam hits the sample, and we typically use 10,000 electron volt electrons. Today we were using 10 kilovolt, 10,000 volts. Sometime today we use some 15,000. And sometimes if we want to look at carbon, we go all the way down to 5,000 electron volts. When the beam hits the sample, it knocks off electrons. And then when electrons go back into those orbitals, they give off radiation that can then be analyzed by the energy dispersive X-ray spectrometer. It does the analysis and it can say, these electrons came back into these orbitals, so the element that we're looking at is carbon, or the element that we're looking at is silicon, or this element is oxygen. So then it can actually tell you that that particle you're looking at is made of so much percent atomic carbon, so much percent silicon, oxygen, magnesium, titanium, whatever. We can't identify low atomic number elements, like we can't see hydrogen, we can't see helium, we can't see lithium or beryllium, but we can see boron and all of the elements above boron. So the point is, we can look at a possible fossil and tell what it's made out of chemically. And that means that we can look for example, nitrogen. Every living thing contains nitrogen. But after it dies, and the nitrogen is typically in the amino acids which make up the enzymes and the proteins, but after that biological entity dies, then what happens over geological time periods, the nitrogen from the amino acids starts leaving, and the carbon and oxygen ratio starts changing. And that's very important, because if the nitrogen stayed trapped in these dead organisms, it would ultimately get trapped in rocks and would all be gone. The same would be true of the oxygen and the carbon and so forth, and we wouldn't be alive, because we need the carbon cycle, the oxygen cycle, the nitrogen cycle, phosphorus, sulfur cycle. We need all of those cycles to bring back things after death so that the material can be used again. Well, the fascinating point is, if we look at what looks to be biological and we see a much higher carbon to oxygen ratio than you have in living organisms, And particularly if you see no detectable level of nitrogen at all, you can say this is absolutely 100% conclusively, with no possibility of deniability or questions asked, not a modern biological entity. It is not a modern contaminant. There is pure, simple biochemistry to back that up. And any biochemist knows, any cellular biologist knows, that even though life is amazingly complicated from a point of view of molecular biology, it is amazingly simple from the point of view of the chemical elements.
We'll talk more about contamination a little bit later. Let's get through the history here.
Oh, wait a minute. Let me say one other thing
Sure.
about that sentence that I just finished.
Sure.
All living things, 98% of every living thing is made of 4 chemical elements: carbon, hydrogen, oxygen, and nitrogen. If you add phosphorus and sulfur, you've now accounted for 99% of everything that's alive. 99%. The rest of the 1% is made of the rest of the group. There are 118 chemical elements, and so we've named 6. That means 114 elements of the periodic table comprise the rest of the 1% of every living cell, with 6 making up 99%. And in fact, you can write a simple chemical formula for life: C4H7O2N1. So for every nitrogen atom in the cell, you have approximately 4 carbon atoms and approximately 2 oxygen atoms. The hydrogen, 7, but we can't measure hydrogen. And the phosphorus and sulfur are much lower in concentration, but much higher than all the other elements. So the point is, from the standpoint of the chemical elements, life is amazingly simple. From the standpoint of molecular biology, the complexity is unbelievable.
Just to clarify on morphology, sometimes you'll see something in an X-ray, under the microscope rather, and it looks exotic, but it's not biological. Something called maybe a biomorph. Is that correct? Do I have that correct?
No, the biomorph term is used to indicate that something has features of biological things, also called morphological biomarkers. And in fact, biomarkers is a lower degree of confidence than...
They're not biological, though.
Well, they can be. They can be.
But
many.
Some aren't.
Yeah, if you see something that looks biological but isn't, for example, if I go outside and I look in the clouds and I see what looks like a dog, I can say, oh, that looked like a dog. Now, if I was a 5-year-old, I might think it was a dog, but most 5-year-olds would be smart enough to know that it wasn't. In fact, I think all of them would actually. But so the point is, there are some things that we look at and we say, okay, it has some of the characteristics of a biological entity, but we can't be sure that it is. And so I'm very, very, I don't, well, it's back to the Diplococcus and the coccoidal forms. There are many bacteria that are coccoidal, but there are so many ways you can make spheres that I, as a general rule, ignore spheres.
So how do you tell the difference between the two? It's just through training?
The difference between...
Something that's biological and something that isn't, but looks similar.
Well, if you're dealing with microfossils, again, you look at the elemental composition. But, again, you can't always tell. That's why it's not a good idea to make your decisions based on structures that can be made both by non-biological and by biological mechanisms. And in point of fact, I've been cautious about that from the very beginning that I started doing this work. I only pay attention to forms that are clearly recognizable as biological, even though in some occasions I can say this has all of the characteristics of a biological entity, but I have never seen anything like this before. Because we don't, there are many people in the world that have never seen an animal called an okapi. But if they went to the Antwerp Zoo and they saw the okapi, which looks like it's got a zebra brown and white coloration of the neck, looks almost like a giraffe neck, but it's on another body, they would say, I've never seen anything that crazy looking before. But they would say, yeah, that's an animal. You follow what I'm saying?
Yeah. So with your research, correct me if I'm wrong, but you have directly observed microfossils in Murchison, Orgeal, Polonnaruwa, Rainbow, and Tagish Lake.
Oh, many more than that.
Many more than that?
Oh my God, yes, many, many more than that.
Get out of here.
Many more than that. We found microfossils in Ivuna. We found microfossils in Murray, in Makoya, in Karunda, in just about every carbonaceous chondrite that I've looked at. I have found recognizable microfossils. In in every nickel iron meteorite that I've looked at, in every stony chondrite that I've looked at, I have never found anything that looks like microfossils.
Okay.
In fact, wait, let me tell another story. Alexei Rozanov came to Marshall, and he brought with him some meteorites that had been given to him by Nazarov, who is was the meteorite expert at the Vernadsky Institute of Geochemistry and Cosmochemistry. Well, one of these particular meteorites we put on the electron microscope, and we sat there for a whole day, and we didn't see anything at all. It was a meteorite called Nikolskaya, and very disappointing. We saw all kinds of interesting rocks, some mineral crystals and things like that, but nothing. And the next morning we started working again, and by about noon, we hadn't found anything. And we were looking carefully. I said, Alexei, what kind of carbonaceous chondrite is this? What? I said, what kind of carbonaceous chondrite are we looking at? I said, is this CI, CM? Well, it's clearly it wasn't CI, but it was CM, CK, CR, the various groups of carbonaceous chondrites, CO, etc. I don't know. I said, you don't know? Nazarov didn't tell me. Oh, so I went and looked, and it was a stony chondrite. It wasn't a carbonaceous chondrite at all. Now, if we were just imagining this, why did we not find anything in this meteorite we thought was a carbonaceous chondrite by just a sheer degree of ignorance? So we did a double-blind, double-stupid test, and we found out that the reason we haven't been finding anything is this is a stony meteorite. The carbonaceous chondrites apparently came from comets. The carbonaceous chondrites contain water and carbon. Water and carbon are absolute essential components of every living thing. You do not have biology without water and carbon. In fact, a lot of people say, well, how about silicon-based life? They just don't understand biochemistry. Silicon-based life is nonsense because carbon makes so many different chemical compounds. It has such incredible abilities and capabilities for forming polymers and so forth that you just don't find in the silicon world. And in fact, most of the Earth's crust is made of silicon, and if silicon life existed, then it should be common on Earth. Now, you might say, but wait a minute, diatoms are silicon life. No, they're not. They're organic life, but they build shells of silica, of amorphous organosilicic acid polymer that they use to make their skeleton structure, essentially. But they're biology is controlled by DNA and RNA, and they have same kind of ATP and NADH and enzymes and proteins that you find in all manner of other living cells.
Okay, so for the lay person here who's heard of this idea of panspermia, okay, the transfer of life, the seeding of life through cometary debris, interplanetary, interstellar, just debris raining down on a planet like Earth and seeding it with the life that's encased in the rock. You have, what, a dozen examples of meteorites that you found fossilized microbes in. Panspermia, case closed?
As far as I'm concerned, case is closed. Absolutely. The idea of panspermia goes way back to the ancient Greeks, Anaxagoras. The idea of seeds everywhere, panspermia. And that concept has been followed by many, many distinguished scientists. The most, in the early 1900s, Spontaneous developed it much more methodically than some of the earlier workers. And the point is, it fell out of favor in the early 1900s because we had just had all of those wonderful discoveries that had just started to be made, and you've got the Darwin work and so forth. And so people thought, well, we know what life is like. We know, and in fact, in the early 1960s, you had the discovery that lightning bolts and volcanic eruptions could give rise to the formation of amino acids. Well, the famous Miller-Urey experiment said, hey, look at this. We can get amino acids from inorganic chemicals similar to what you find in the ancient Earth atmosphere and lightning bolts and volcanic materials. So we've solved the problem of the origin of life. And in fact, a lot of people believe that, okay, it was just a few steps further and we would understand how, when, and where life originated. And that was widely believed. And in fact, many still believe it, but it's complete nonsense because the Miller-Urey synthesis experiment, they succeeded in making some amino acids, but every living thing requires 20 proteinogenic amino acids to make the life-critical proteins and enzymes. And actually, there are two others that are used sometimes. So 22, 20, whichever you want to call it, there is this set of amino acids that you got to have for biology. Absolutely got to have all 20. Some cases you can get by without the other two. But basically, when you make them non-biologically, you can't make all 20 protein amino acids. And even worse than that is homochirality. Louis Pasteur discovered the phenomenon of biological homochirality. Now, that takes a little bit of explaining. If I give you a pair of gloves and you take them and you stick your right-handed glove on your left hand, wait a minute, this thing isn't working because the palm is on the other side. But if you turn them around and you put your right-handed glove on your right hand and your left-handed glove on your left hand, they fit like a glove. Well, it turns out that a vast array of the chemical molecules are chiral in that the compound has two different shapes. It has exactly the same chemical composition, but they occur in mirror images of each other. And this was discovered by Pasteur when he studied wine dregs, and he found out that the wine dregs have a chemical like sodium paratartaric acid, and in these dregs, it rotates the plane of polarization of visible light in a particular direction. The ones that rotate the plane of polarization clockwise are called the D form, and the ones that rotate it counterclockwise are the L. Well, it turns out that every living thing, every amino acid in every living thing is an amino acid that will rotate the plane of polarization counterclockwise, or it's called an L-amino acid. Every sugar in your structural carbohydrates, every sugar in your ribose and deoxyribose in every DNA molecule in every living thing is a right-handed sugar. It rotates the plane clockwise. And the reason that's critical is if you started making a helical RNA molecule and it's rotating like so, and then you tried putting in a sugar that wants to cause it to start spiraling the other direction, you're obviously not going to get a functional DNA or RNA molecule. And the point is, this phenomenon of homochirality, Louis Pasteur said was the signature of life. And I agree with that 100%. All biology that we know functions on homochirality. And the fascinating point is that if you make these chemical compounds by non-biological techniques, you get equal amounts of DNL, equal amounts of right-handed and left-handed. But biology, when it takes in this material, it selects the one that it wants to use and it throws away the other. So that's the reason you can eat sugar that is the wrong chirality and it'll taste just as sweet as ordinary sugar, but you won't get fat because your body doesn't like it and it will not put it into its cells.
Where can one get this sugar?
Tagatose was one of them that I think, but
Tagatose,
there are a number of these sugars that are of the opposite chirality. And
So this is not artificial sweetener. What's in Diet Coke?
I think it's aspartame.
Okay, it's not aspartame.
No, it's not aspartame. And in fact, Dr. Pakuta and I did a study, which was very interesting. Brilliant guy by the name of Paul Davies. You may know Paul C.W. Davies, who's written many wonderful books. Several years ago, Paul Davies organized a workshop called Life as We Don't Know It. And one of the questions was, what happens if extraterrestrial life is built different? What happens if it's completely alternate chirality? What happens if you've got biology that instead of using D sugars and L amino acids, use L sugars and D amino acids? Could we tell the difference? And so Dr. Pakuta and I participated in this workshop that he had. And one of the things that we did beforehand is we had all kinds of strange bacteria that I'd collected all over the world. So one of the questions we had is, what happens if we try to feed these bacteria the wrong kind of sugar? What do? Can they eat it? And so forth. Well, one of the amazing things is we did this study and we found that by and large, they wouldn't consume L sugars or D amino acids, except one of them, Anaerovirgula multivorans that we had discovered from Mono Lake. Anaerovirgula multivorans, we called it that because we called it multivorans because we thought of it as a microscopic goat that would eat darn near anything. And we discovered that Anaerovirgula multivorans was capable of consuming and growing on L-arabinose. And that was shocking to us. In fact, it's still a mystery because we thought it might be using a mechanism of flipping the L-arabinose, which is a sugar, from L to D, and then using that to grow. But we found out that it couldn't grow on D-arabinose, but it could grow on L-arabinose. So there were some very, very strange things that we encountered in this set of studies. But that was what was the purpose of this whole symposium, was to find out, okay, what if you find life and it's growing in a completely alternate way? And that's the essence of an experiment that I proposed with Gil Levin, to look for life on Mars, to have his label release experiment that you know about very well, but to do what we call TWEAL, and to have nutrients. One side would have D amino acids and L sugars, and the other side would have L amino acids and D sugars. And if in the little arrow, when it sticks into the regolith of Mars, and then you put you put nutrient media of the alternate kind, if it is biology that's like Earth life, the one that is seeing the L amino acids and the D sugars will show metabolism and the other won't. If it's biology that is alien, the L sugars and D aminos will show action and the others won't. And if you get the same response from both sides, it is chemistry, abiotic chemistry. So that would have made it possible. We're still hoping to fly this by maybe on a SpaceX, but that delivered to Mars would make it possible to tell, do we get a reaction like was obtained by Gil on Viking? If the answer to that is yes, does it occur in the same way both with the two chiralities? If the answer to that is yes, then that means that the people that argued that it was made by metalloperoxides were right. But if the answer is that you get action on D sugars and L amino acids, it would mean, and none on the other, it would mean, hey, we got life on Mars that works exactly the same way as Earth life works. If it's opposite, it would mean we got life on Mars that works in the opposite direction. But Gil didn't pay attention to chirality on the Viking experiment. So if it was life that worked on the alternate chirality, the experiment would have given the same result, because he had both D and L sugars and both D and L amino acids. And the reason he did that was he said, we don't have any idea, A, if there is life on Mars, or B, if there is life on Mars that is like Earth life, or C, there is life on Mars that is entirely different. So in order to optimize his chance of detecting biology, he flew a label release experiment with both L and D sugars and L and D aminos. And that was what caused the criticism. It was argued that, well, this could be produced by chemistry.
All right, I'm going to run through a brief history of the discovery of microfossils and meteorites from 1961 to present day. Okay, I'm not going to get everything. It's not comprehensive, but just given our conversations. Let's rewind the clock to 1961. Dr. George Klaus and Professor Bartholomew Nagy, they published a paper titled A Microbiological Examination of Some Carbonaceous Chondrites. And I'm quoting from that paper, and it says, microscopic sized particles resembling fossil algae were found to be present in relatively large quantities in the Orgyle and Ivuna carbonaceous meteorites. Skipping forward a bit, we are of the opinion that these observations suggest that the organized elements may be microfossils indigenous to the meteorite. So this was in 1961. Of course, this caused a big stir. And in response to that paper, we have these other two guys, Frank Fitch and Edward Anders. Okay, they published a few papers in response to that one. First one, search for organized elements in carbonaceous chondrites. In response to that one, they said the possible occurrence of life forms in meteorites, as reported by Klaus and Nagy, has aroused considerable interest and discussion. Because of the far-reaching implications of these findings, we have sought to confirm them. To date, our efforts have largely been unsuccessful. And this was in 1962, the following year. So they're saying, well, we haven't found what they found. So they're suggesting that their discovery was incorrect. And they followed on to that next year in 1963 with another paper, Organized Element, Possible Identification in Orgyle Meteorite. And they say, quote, ragweed pollen stained by the Gridley method, becomes distorted so that it resembles Klaus and Nage's type 5 organized element, a particle found in Gridley stained preparation of the Orgeal carbonaceous chondrite. So they're basically saying you can attribute what they found to
Ragweed pollen.
pollen contamination.
Yeah.
Okay. Fast forward one more year, 1964. They have a paper literally titled Contaminated Meteorite. And this is when things start to get really sticky with this whole subject here. I'm going to quote from this paper. One stone of the Orgeal meteorite shower contains an assortment of biogenic materials, coal fragments, seed capsules of the reed Juncus conglomeratus, other plant fragments, and an optically active water-soluble protein material resembling collagen-derived glues. This sample, they sum it up, this sample seems to have been accidentally or deliberately contaminated shortly after the fall of the meteorite in 1864. And this, so what Fitch and Anders are arguing is that Klaus and Nage's discovery of microfossils in a meteorite was incorrect, and on top of that, they're trying to smear this whole subject by suggesting that because they found a deliberately contaminated sample of the Orgeal meteorite, well, that just makes everything messy, right? I'm going to list two more things, and then you can respond to all this, okay? We have another team of people, W.C. Tan and Sam Van Landingham, okay, and they published in 1966 their paper, Electron Microscopy of Biological-like Structures in the Orgeal Carbonaceous Meteorite. Quote, the consistent pattern noted in the ultrastructure of these organic bodies seems to indicate the presence of an organization system reminiscent of biological structures. Again, this is in 1966. Now, we're going to fast forward a whole lot of years here to sort of a comprehensive analysis of this back and forth, this historical back and forth. A paper published in 2014 called The Orgeal Meteorite, 150 Years of History. Quote, despite the clear disconnection between the Anders study and the organized elements, between Anders and Klaus and Nage, the discovery of contamination helped to cast considerable doubt on the reality of the extraterrestrial life form. So this is basically saying, because there was this contamination controversy, this whole subject is now considered to be taboo. No one wants to touch it because everyone just thinks of this controversy brought up by this, what they found to be deliberate contamination. So, do I have that right?
Yeah, you have it exactly right. Let's go back to the original argument. When Klaus and Nage made their report of possible microfossils in the meteorite, the Orgeal meteorite, and Ibuna, found them in both of them. That actually followed some other work, and I need to give some prehistory of this. Bartholomew Nage was a petroleum geologist working for Esso, and he had been studying oil shales. And the reason he was studying oil shales was because his oil company wanted him to be able to tell them when they pulled up rocks from a particular strata, what was the chance that above or below that set of rocks they would find petroleum. So his study was related to money. How do you find whether you've gone through the petroleum deposit and you're at a lower strata, or whether you haven't gotten to it yet? And that also included gas and, natural gas and so forth. Well, he was doing this with a new instrument called a gas chromatograph mass spectrometer. And he had seen that way back in 1864, after the meteorite fell, the studies that were done by the scientists in that day said, wow, this stuff looks organic. Wow, this stuff looks like it was made by biology. And oh my God, these meteorites have carbon, hydrogen, and oxygen compositions just like coal, lignite coal from Rignul and so forth. And so the early scientists said, does this indicate there is biology on the parent of this meteorite? Now, this was studies done by scientists in France that were the leading chemists of the day by far.
What year?
1864 is when the meteorite fell, or it fell May 14,
And that's when these
1864.
scientists were studying. They were studying this then, and that.
Oh my gosh, yes, 1864, and they were writing about this. This looks like this is organic, and in fact, they even said such things that we think this was made by biology. 1864.
They were saying that in 1864.
Yeah, in 1864.
They just had an intuition.
Well, no, they saw they were accepting of the idea that coal and peat, lignite coal, bituminous coal, anthracite coal, came about from biology. Didn't come about from inorganic rocks. It came about from biology. And here they find coal-like material in this meteorite that had just fallen. And then when they looked at the Allan meteorite, which was a similar one, they found, yes, it had similar composition. And both of these contained something else that was very special. In fact, when they first started studying the Allan meteorite that landed in 1806, the scientists studied it, almost threw a sample away because he found it contained water. Then he found, other scientists have found water as well. These carbonaceous meteorites contain not only carbon, but extraterrestrial water. So water is the prime essential, water and carbon are the prime essences of life. You cannot have life without carbon and water. You can get around with a lot of other things, but you do not have biology without carbon and water. Again, it's that C4H7O2N1. So they then published these results, and the studies then were sort of fallow for a period of time, and not much was done until Bartholomew Nage came along, and he saw these organics in the samples he was looking at from the meteorite. And he thought, gee, maybe this was made by biology. So he brought in George Claus, who was a renowned microbiologist at State University of New York, and said, this is what I've found. Let's examine this and see what we can find. And so they did microscopical study, and they found a series of things that looked biological, both in size and shape and morphological detail. So they published this simple little paper. Hey, we think there is a possibility we found biology in these two meteorites. And it caused a bit of an explosion when the paper came out, and there was all sorts of yelling and screaming about it. So the controversy didn't start later, it started instantaneously. Ed Anders was the director of the Meteoritical Society, one of the world's greatest experts on meteorites. And here were these crazy guys saying, we know something about meteorites you don't know. How outrageous could you be? So therein started this debate, and it had become somewhat heated when Harold Urey, Nobel Prize winner, decided that there should be a meeting at the New York Academy of Science to try to resolve these questions. So they set up a meeting that was held in 1962 at the New York Academy of Sciences, and they invited distinguished scientists from all over the world to come and participate in this. Sam Van Landingham, Tash, Palik from Eötvös-Loránd University, Robert Ross from the British Museum, all came there to discuss and assess the nature of this result. And Urey, after looking at the results, he said if these things were found in terrestrial rocks, there would be no doubt whatsoever that they are biological. But meteorites are primarily igneous kind of rocks rather than sedimentary, and we know that biology is associated with sedimentary rocks. Of course, in 1962 or 1963, nobody had any idea at all that you could find biology in in hydrothermal vents, which are volcanic. Nobody would have believed that. Everybody would have said that's absolutely impossible. So anyhow, the other thing that is important in this, when George Claus and Bartholomew Nage made this publication and it was criticized, well, Claus was a microbiologist. He wasn't a palynologist. Palynologists are the kind of people that study pollen. Pollen wasn't his field. So, okay, these two guys say what we're looking at is pollen. Well, is it? And being logical scientists, they went to Tucson, and in that year was the first International Palynological Society meeting. And they brought in a bunch of the slides, and Bartholomew Nage brings over these distinguished palynologists and says, we've got some pollen, can you tell us what kind this is? Now, instead of them looking at the slides and saying, you idiot, that's ragweed, which they would have certainly done if it was ragweed pollen, they said, this isn't pollen. We don't know what it is, but it's not pollen. So now then, they're presenting it to pollen experts, not meteoriticists. Ed Anders doesn't know anything about pollen, and quite frankly, neither did Fitch. But they came up with that as an explanation to do away with the result. Well, so after their critical paper about stains and so forth, Bartholomew Nage and Claus did enormous studies of pollen and various other types of stains on their organized elements, as well as different kinds of pollen grains, and were not able to show that these stained like pollen. And so when they were told by the pollen experts, we don't recognize these, the question was, if they're not pollen, what are they? Well, maybe hystricospheres. Well, what do we do about that? Who knows anything about hystricospheres? And they were told Robert Ross, the keeper of botany at the British Museum, was one of the world authorities on hystricospheres. So they sent slides to Bob Ross, and he looked at them, and he says, no, these are not hystricospheres. Well, what are they? And his response was, I don't know. But Ross was a curious scientist, as all scientists should be. And Ross was in a unique position. He was keeper of botany at the British Museum. So he knew everybody there. He went over to the one in charge of geology and said, can I get a piece of the Orgueil meteorite? Okay, sure. I mean, they had bunches of it there. So the keeper of geology gives to Ross about the size of a golf ball, a fusion-encrusted Orgueil meteorite, completely spherical, fusion completely around. I mean, I tear up when I think about this, because Ross then took this pristine, absolutely precious, I mean, it was like the Hope Diamond of meteorites, and he took a scalpel and carved the fusion crust off the darn thing. Yikes. Anybody that did that today would be worthy of being shot. Well, maybe not shot, maybe just the electric chair. But he carved it off to get to the inside. And then he dropped this precious piece into liquid of different densities, and using the density separation method, different pieces floated at different levels in this cylinder tube that he was using, and he extracted these things from different levels. And while he was at this meeting in New York, he reported that he had found small mushroom-shaped organic structures that had come out of the meteorite. Well, this was a very exciting report, because this indicated that Bob Ross thought he was dealing with biology, and that the kind of things he was looking at were maybe some kind of fungi or something like that was very tiny, but shaped like little mushroom structures. Well, I had talked to Bob Ross later because I had discovered diatoms that everybody believed were in the British Museum, and he came to Antwerp and worked with me for a week on the collection of the Reverend William Smith. So I got to know Bob Ross very well. And I talked about the Orgay meteorite and Ivuna and this meeting with him. And so as a result of that, at the time David McKay made the announcement, I thought, this is nuts. Everybody knows there are fossils in meteorites. I knew it. Why didn't everybody else? What was going on? Well, I was completely unaware that this debate had gone to the kind of incendiary level that it had, and I had never read the contaminated meteorite paper. I didn't even know of its existence. But what had happened was, after they had announced this discovery, a lot of scientists started studying the Orgay meteorite, and they started finding interesting things. They started finding amino acids. They started finding porphyrins. They started finding pristane and phytane. Well, you might say, what in the heck is that? Pristane and phytane are the breakdown products of the chlorines of chlorophyll. And vanadium porphyrins are like the porphin ring that is at the head of the chlorophyll, which contains magnesium when it's living in a plant or in a tree leaf, or it's vanadium when it's long dead. And if it's in a red blood cell, that porphin ring contains an iron in the nucleus, and that's what transports the oxygen as a part of the photosynthetic and the process of getting oxygen around your body through red blood cells. So we're talking biology. We're talking pure biology. Now, the fact that they had found these things meant, well, there's more than just the shape of things in order to say that there was biology in these meteorites. But when this paper came out, and in addition to that, they had found coal-like material, which is called kerogen. When that paper by Anders and Fitch came out, called Contaminated Meteorite, it destroyed everything. First of all, of course you can find amino acids. Somebody planted pollen grains in there. Of course you can find kerogen. Somebody put coal in there. Of course you can find pristane and phytane. Somebody put pollen in. Well, of course, that isn't quite right, because you don't find pristane and phytane out there in the grass. After the grass dies and has been dead for many millions of years, then it decays and loses various portions of the chain, and that's where you get pristane and phytane. So
wait, Fitch and Anders,
yeah.
They, in this contaminated meteorite paper, they examined a sample from the Orgay meteorite that they got from where?
From Montauban, and one of their people went there and picked it up. And then they claimed that they had found that somebody had drilled a hole in it and had put in this stuff, probably in response to the debate of organic formation of life or abiotic formation of life, and that this unseen person back in the 1800s did this, and then decided not to go through with his hoax and put it back on a shelf, and
in a museum.
Their guy happened to pick up the right one, the right contaminated meteorite. And in so doing, all of a sudden, studies of microfossils in carbonaceous meteorites was Piltdown Man. Anytime somebody is dealing with a hoax, it is absolutely deadly to their scientific career.
So unbeknownst to Fitch and Anders, their sample that they analyzed was deliberately contaminated 100 years prior.
That's what they claim.
That's what
I
they
don't
claim.
buy it for a nanosecond.
You don't buy it?
Of course I don't buy it. I believe someone in that group did the contamination intentionally and then announced they had discovered a contaminated meteorite. And the reason I don't buy it is, what are the chances that they would go there and happen to pick up the one piece of the Orgay meteorite that somebody had contaminated? And not only did they contaminate it, they went to great pains, because they had not only put these things in there, and just the right things to destroy the evidence that was gained post-1960, just the right things. And in addition to that, they had then so cleverly mixed the powder that they got out of the hole with this collagen-type glue and put it over the surface to where it looked like a fusion crust, where unless you examined it carefully, you would not have any idea that there was anything wrong with this piece of the rock.
So this is just where they patched over.
Yeah.
Someone had drilled in.
They drilled a hole.
So what are the chances of, you're saying, what are the chances of them finding this one particular patched over hole?
No, getting the one fossil, the one piece of the rock that was...
Sure, but even going one step further, what if they had just simply examined the other side and not even found that hole? How miraculous is it that they found the drilled hole in the
and it had fusion crust over the top of it. And what's more, the reed that they found, you called it Juncus conglomeratus. It's a particular kind of reed. Genus Juncus, species conglomeratus. Well, now by this point in time, the argument had become very heated. And after they did the contaminated meteorite paper, when Klaus or Naj would give a paper at a scientific meeting, one of the Fitch and Anders group would stand up and say, "This is nothing but conglomerated junk, Juncus conglomeratus." So the point is, let's look at motive. What motive would they have had to do this? They destroyed the Naj and Klaus work. In fact, George Klaus lost his position at the university. In fact, he told others that the discovery of microfossils in the Orgay meteorite, of organized elements, which they were forced to call them, saying, we don't know if these are really biological. We know they look interesting, but we're not saying they're life. Well, after he was fired, he became very bitter, and I was told by Sam Van Landingham that George Klaus concluded that his discovery of possible evidence of microfossils in meteorites had, quote, destroyed his life. I mean, that's serious. So the point is, to win the argument and win the scientific battle, it was very helpful to publish that paper called Contaminated Meteorite. And I might add, if you go on Wikipedia this very day and you look at Orgay meteorite hoax, you will find all sorts of details about the contaminated meteorite paper. And that ties back to Alexei Rozanov. Alexei Rozanov had started studying the Orgay meteorite, and he had found what he thought were microfossils in it, and he had written a scientific paper, and it had sat on his desk for almost 3 years. And he told me he did not dare publish it. He was afraid to publish it, and he only submitted it to the journal after a Mars meteorite result was presented and accepted as, this is sufficient evidence to start the scientific search for extraterrestrial life, the beginnings of astrobiology.
Let's come back to Rozanov in just a second, okay? So we've mentioned this meteorite, I'll say Orgueil, that's how it's spelled. Us Americans, That's what we say. Now, you're a French major. How is it pronounced?
Orgueil.
Okay, I'm taking that.
Orgueil.
All right.
Okay.
All right. So just real brief history of this particular meteorite for those for those who have never heard of this. Okay, just give us a brief history of its discovery.
Okay, it wasn't discovered. It saw as a fireball. It was seen as a giant event over the south of France on the 14th of May, 1864. There was a huge ball of light that passed across the sky, first seen over Spain, and then it went all the way across southern France. The light was seen almost as far away as Paris, which is very, very far away, several hundred miles. I don't remember the exact distance. But the sound of the explosions was seen over a very broad, was heard over a very broad region. Many of the villagers of the little village of Orgueil and Noik and Kamsas, several of them thought the world was coming to an end. Several of them thought there was an earthquake. Others thought that Madame de la Pillaroque thought her chateau was on fire. There was such bright light on the inside of her castle. She thought it was on fire. People from all around the area who had seen this wrote letters to the scientists, the academicians of the day, and described what they had seen and where and when and what it looked like. And so from those letters, it was possible for people to calculate the orbital parameters, and it looks like it was from one of the Jupiter family of comets.
Have you read these letters?
Yes.
Of course you have.
Yes, of
Go
course
ahead.
I have. In fact, I've read all of them. And
Where can you find these letters?
I went to Compte Rendu. That's where they were all published, and published in the original French. And so I downloaded them from this journal from most of them were published in 1864, right after the meteorite fell. And they describe fascinating things. One of the things that they describe is one of the scientists wanted to measure the density of the Orgueil meteorite. Well, density is what is the mass per volume, so many grams per cubic centimeter. Well, he could easily measure the number of grams by just putting the meteorite on a scale. And he wanted to know what was the exact volume of the meteorite. So his plan was, you can get volume by just having a graduated cylinder, and if you drop a rock in it, when it goes in, the old, how much water does it displace? You know, the principle that it's going to displace the amount of cubic centimeters of water that is exactly equal to the volume of the rock that you drop in. So he dropped a beautiful piece of Orgueil meteorite into a cylinder of water, and it disintegrated. It dissolved. What happened is, at that point in time, the scientists began to realize that this meteorite was actually primarily interstellar dust particles that were cemented together by water-soluble salts, mainly magnesium sulfate, good old Epsom salts that you soak your feet in when they're tired and not feeling well. So one of the dominant minerals of the Orgueil meteorite is magnesium sulfate, and it's magnesium sulfate hexahydrate with MgSO4 times 6H2O. So, and you have some with 7 waters and some with 5 waters, but most is with 6 waters. So the point is, meteorite contained carbon, the meteorite contained water, and so that led Klaus and Nage to look for biology. But when Fitch and Anders reported the contaminated meteorite, they had established that this was a complete hoax, a Piltdown man, and that totally destroyed all scientific research, except not all, because there were some people that did work after that because they were unaware that, oh, these guys said so-and-so. Or maybe they were aware and said, no, we don't buy it. I don't know which it was, but the point is this caused the study of microfossils in meteorites, as Manfred Szydlowski called it, to be taboo. And that's why Alexei Rozanov didn't dare publish his paper until there was this explosion about, gee, there are microfossils in a Mars meteorite, nanofossils, in Allan Hills 84001. And that's when I said, This is nuts. Everybody knows there are fossils in meteorites, and that's why I got a piece and started looking for them.
The Orgel meteorite that fell last time we spoke, you said it was covered in frost.
One of them was.
One of the pieces was covered in frost.
Pieces.
One would think it comes down, it's hot. Why would it be covered in frost?
Well, that's an interesting point. A lot of people believe that meteorites that fall through the atmosphere are hot. Well, they are, and they aren't. It's like fried ice cream. What happens is the meteorite, the Orgel meteorite, it is a relatively low density carbonaceous chondrite. The Apollo command module is a relatively low density vehicle. When the Apollo astronauts came back from the moon, when they entered the Earth's atmosphere, the temperature on the heat shield got to about 5,000 degrees. The flames came up around and formed this giant plasma around the Apollo command module coming in through the atmosphere. Same thing it did on the heat shield of the shuttle. And on the SpaceX vehicles and so forth, anything coming in from space, traveling at a velocity of anywhere from 20,000 or 30,000 miles an hour, is going to reach an extremely high temperature. But back to Apollo, when it came in from the moon, it did aerobraking, because the atmosphere, when it's getting it very hot and boiling away this ablative layer, also slows it down. So the heating only lasts for 30 seconds, 45 seconds, and it gets very hot, but then it's slowed down where it's no longer being heated by friction, but now it's going into the part of the atmosphere. You get in a plane, you go up to 40,000 feet, it's 40 degrees below zero outside. So it comes through a layer of the atmosphere going slower that is much colder. So basically, when these meteorites land on Earth, they're pretty much like a shuttle landing or an Apollo command module landing. If you go out and stick your hands on the tile of a shuttle, it's going to be hot. But the shuttle isn't made of extremely cold material on the inside. And the temperature on the inside of the meteorites, their waters are in the form of ices and in frozen hydrated minerals. But the entire interior of the Orgel meteorite was probably somewhere between 150 and 200 degrees below zero. And the outside, a thin layer, maybe a millimeter or two, gets very hot. And it stays hot for a relatively short period of time until it lands. And actually, if there have been cases where people have picked up one of these meteorites immediately after they landed and burned their hand. It happened in Polonnaruwa. It happened in Murchison. A person burned their hand on a piece of Murchison. One came through a roof of a shed in Murchison, Australia, and caused the hay that it fell on to start smoking. Didn't burst it into flame. That means the temperature was below Fahrenheit 451, the old book, Bradbury book. So, and some pieces landed on a golf course in Murchison, and they scorched the grass. They didn't penetrate deeply into the soil. They landed on the green and hit and bounced and rolled, because by the time they got to the ground, they were going at terminal velocity. So they were traveling 100 and something miles an hour. Like if you throw a baseball out of an airplane, it's not going to be going 1,000 miles an hour when it hits. It's going to be terminal velocity. If you jump out of a plane and your parachute doesn't work, you're going to be arriving at the ground at terminal velocity, which will be a little bit different if you do a swan dive or if you spread your arms out and try to slow yourself down. But wait, let me get back to the frost.
Okay.
Madame de la Pillotte, when the one that thought her castle was on fire, walked to her garden path the next morning, and there was a white rock lying there. And she looked down and inspected it and found that it was covered with frost in the south of France on the 14th of May, the 15th of May now, 1864. You don't get frost in the south of France in May. It doesn't happen. So what that means is that The piece of meteorite that was lying there, there had been a thermodynamic battle. The hot fusion crust cooled to room temperature and then kept getting colder and colder until it went below the condensation point of the water. So water from the atmosphere condensed on the outer surface just like it would on a cold bottle of Coca-Cola. And then, because the interior was even colder, it froze on the outside and formed a layer of white frost. And that is, to my mind, proof of a way in which biology could be transported, because life on the inside could be frozen inside the ices, and when it lands in an ocean or a lake or a stream and then disintegrates, it could release these biological entities. If there are any alive, they could come out into the ocean and start living and saying, this is a good place to call home. So this is a kind of panspermia that we refer to as typically lithopanspermia. I like to talk in terms of something that we're calling wet panspermia, because in fact, the ideal situation is to have things that are traveling from one star system to another, from one planet to another, from one stellar system to another, or from one galaxy to another, living and growing and reproducing and dying on the inside of the body that they're traveling in. Just like we are doing the same thing. We have biology on Earth that has been here for 3.2 billion years, the cyanobacteria. And they're still here. They still look the same, because even though the ones that were alive 3.2 billion years ago are long dead, the offspring, millions and millions of generations later, are continuing to grow and pass on this DNA.
Because of this controversy surrounding this contaminated meteorite paper and decades of back and forth saying, well, it's just a big hoax, and it was rendered a taboo subject to even study or even talk about it. No one wanted to even touch it. But then in 1984, we discovered the Allan Hills meteorite in Antarctica. We've talked about this before. It wasn't until maybe a decade later, where it was publicized and Bill Clinton, the White House lawn, that sort of thing. So it really took until the Allan Hills meteorite to really revive the public's awareness of this fascination of microfossils and meteorites. Now, Allan Hills is certainly, the last time we talked about this, Allan Hills, I mentioned the Allan Hills is, as far as the public is concerned, it is the most well-known meteorite. Now, most people don't know all these other meteorites, which is why we're talking about them today. If you can briefly tell us, number one, why did it take 10 years for us to understand that the Allan Hills meteorite had microfossils in it, or possibly microfossils in it? I mean, and why did it ultimately end up with Bill Clinton on the White House lawn?
Well, the first thing that happened was when the meteorite was found, it was brought to the Johnson Space Center, pieces of it. I don't know where all of it went, but pieces went to the Johnson Space Center, and it was classified as a SNCC meteorite, which means a type of sugartite, noctilite, chausignite. Those are the groups of meteorites from Mars, and the Allan Hills was identified as being a Martian meteorite, based on the oxygen, the analysis of gases within the meteorite. So they knew Allan Hills was from Mars, but it wasn't until David McKay started looking at it and found things that looked like nanofossils to David McKay, and they then started saying, whoa, could this be biology? And they got other people involved, like Dick Zare at Stanford, and he looked at the polycyclic aromatic hydrocarbons, and then you had the study of the magnetosomes that was done. So when all of these pieces of evidence were brought together, they came to the conclusion that the sum of these things supported biology. And when they...
How soon after discovery?
Well, it was studies that were started in late 95, early 96.
It took them that long to start studying it?
Oh, yeah. I mean, this
Why?
kind of study.
They discovered
because
it in
nobody would
84.
bother look at a meteorite. Why would anybody do that? That would be crazy.
So it took them that long to even look at it?
Yeah, to look at it with a microscope, absolutely.
Oh, okay. So
absolutely.
So they looked at it with a microscope. How did it end up with Bill Clinton on the White House lawn? Quick story, quick version of this.
A real quick story. Well, it's in a book.
Yeah.
Forgotten the title of the book. I mean, the author of the book, but it's in public.
Right.
Dick Morris, who is on TV today, he was the chief advisor to President Clinton. There was a convention about to be held, and Dick Morris received a phone call while he was in the Mayflower Hotel, and he was, let's say, with a lady of the evening in a hotel.
Female companion in a hotel.
Female
Got it.
companion in a hotel,
Got
yes.
it.
But anyhow, in order to impress this lady, he invited her to listen in on the conversation. So she listened in on the conversation between Dick Morris and the President of the United States. And afterwards, she went to...
And the conversation was?
The conversation was that the President of the United States was informing Dick Morris that NASA had evidence that they had found microfossils in a meteorite from Mars.
Clinton is telling Dick Morris, NASA told him they found a
NASA's
microfossils.
found evidence of microfossils in a meteorite. And she hears this.
Okay.
Well, she then went to a tabloid. And I don't remember whether it was the Globe or the National Enquirer,
Sure.
one of those tabloids, and went in and told them that she wanted to give them a story. And they wanted to know what it was about. Well, I know something only 5 people on Earth know. Really? That's interesting. And she then allowed us how she was with the assistant to the president when he was informed by the president that NASA had found evidence of life on Pluto. And they said, what? Wait. No, wait. It was life on Mars.
Okay, so she goes to the tabloid.
And she had the story kind of messed
Does
up.
the tabloid publish this?
Well,
Or does the president get ahead of this?
No. The president got ahead of it because what happened was someone from the tabloid called NASA headquarters and said, we're getting ready to do a story about NASA finding evidence of biology on Mars.
Okay.
Would you like to comment on that paper? And the response they got, I have no idea who gave this response, but whoever gave it was an absolute genius. They said, he or she said, we can't comment on that because that paper is under embargo. Oh.
Boom.
Oh.
They've got him.
Boom. We can't talk about it. That paper's under embargo.
Okay, so that confirmed it. Fast
Okay.
forward, Bill
So
Clinton.
then what happened was I don't know how much they paid her. They paid her for the story. And NASA found out that they were going to go with this story in the tabloid. And it appeared in the tabloid that following Monday, I think, was when it was published. But when that hit, that NASA Public Affairs had word that, whoa, the story is out. And they're going to run with it. And what are we going to do? Because, all right, if we cover this up, it is not only did NASA find life on Mars, but NASA has lied to the public and refused to reveal it, and therefore it's a cover-up. The cover-up is always worse than the crime.
In the wake of all this, this is right around the time when you got started in astrobiology. In the wake of this, okay?
Exactly.
Now you had discovered. Let's get to your collaboration with the Russians, and I'm gonna give a little bit of a history here. You tell me if I got this right, okay?
All right.
So, in the wake of all this, you discover that there is a gentleman in Russia by the name of Dr. Alexei Rozanov, who had already been looking at microfossils and meteorites and had a paper on his desk for a few years, afraid to publish it because he knew the history and what that could possibly do to his career. Right?
Mm-hmm. Yeah.
And he heard about what's going on with Allan Hills. Turns out the Russians were also looking to microfossils and meteorites, as we were just discussing. And ultimately, you connected with Rosenoff and you started working with him, and you've published papers with him. We'll talk about more of this in a second. I'm just going to give an overview here. Okay. You've also mentioned a gentleman by the name of Georgy Zavarzin, who I understand to be the premier microbiologist of Russia. And at one point in time, you showed him some of your work, and he immediately identified them as cyanobacteria. This is as far back as 1997, if I understand things correctly. Another gentleman by the name of Eric Galimov, director of the Vernadsky Institute of Geochemistry and Analytical Chemistry, Russian Academy of Sciences.
At that time, it was geochemistry and cosmochemistry, but it's now geochemistry and analytical chemistry.
See that, folks? This man knows what he's talking about. From 1992 to 2015. So you discovered through David McKay that Rosenoff was working on microfossils. You got in touch with Rosenoff and thus started your long collaboration with a team of Russian scientists specifically looking at microfossils in meteorites. Now these guys aren't, now look, today us Americans, you mention Russia and it's going to conjure up a whole lot of emotions, all right? We're not going to get into that, but we have to acknowledge that there is an inherent distrust among Russians for how we view Russians, okay? They're known for doping at the Olympics. You know, we have a complicated history with them. We're not going to get into all of that, but whenever we hear, us Americans, because we're so entitled, whenever we hear of somebody who is credentialed in another country, inherently we don't think it means as much. Okay, so you've worked with these Russians. They're no jokers. They're no amateurs. They know what they're doing. And you, along with them, over the past 2 decades, have published papers with photographs. People can go look for themselves. Okay? Microfossils in meteorites. Do I have that right?
Yes, indeed. Let me, well, I'll slightly clarify a couple of things.
Yes.
What happened was when this announcement came out, and I said, everybody knows this, then I thought, well, maybe I've heard it talked about, but I don't know for a fact that there are microfossils in meteorites. So I contacted Michael Farmer, a very respected meteorite dealer, and I paid $100 to get a 1-gram piece of the Murchison CM2 carbonaceous meteorite. That arrived, and I took this little cube about like the end of your finger and took it over to the scanning electron microscope where I was today. And with Greg German, we broke it open and put it in their environmental scanning electron microscope. Within an hour, somewhat less than an hour, we're looking along, and here's a little teeny mushroom sitting in the rock. Hot dog, that's what we're looking for. A mushroom-shaped thing, kind of like, was found by Sir Robert Ross. Oh, okay, this is what he was talking about. But it's very, very small, and so we enlarged it to fill the field of view of the monitor screen. So we were about 30,000 times magnification. And since we wanted to know what the various elements were, and we had not done any work at all with this before, we were looking at it with radiation of 30,000 electron volts, which we never use anymore, but we did then. So we could see heavy elements and so forth. So we're focusing, getting it just perfectly framed, scoot it this way, scoot it that way, and all of a sudden, shh, and it was like it was there and it just vanished. And there's a little hole in the rock where it was, but it was gone. And so basically what we did is this was made of kerogen, and we put such an incredible amount of energy into that structure that we burned it up. We literally vaporized it. And so the first time I find an alien life form, I pull out my ray gun and shoot the heck out of it. Well, my gosh, we had found this in less than an hour. Oh, they've got to be common, so don't worry about it. We blew that one up, but we got a picture of the hole. I've got it on my computer. We got a picture of the hole, and we'll find more of them. Well, that That was late 1996, and since then, I've spent thousands of hours on electron microscopy of meteorites, and the total number of fossils that look like that I have found is exactly 0. That was the one and only one I ever saw in my life, and
so
we destroyed it. So what happened is I got a bunch of pictures and wrote a paper. And the paper that I wrote was on instruments, methods, and missions for the investigation of extraterrestrial microorganisms. And I sent a copy of that paper to David McKay to get him, to ask him if he would be so kind. I'd call him on the phone. Will you be so kind as to read this and let me know if you see anything that should be corrected? You know, I was basically asking a NASA expert to give me feedback. Have I said something that sounds stupid? And so forth. And when David got the paper, he called me up and he says, I got your paper. You know, the Russians are doing the same kind of thing. I know. I said, I didn't know that. Yes, he said, Zhimur and Rozanov are working on similar kinds of things. They sent me a paper for me to look at as well. I said, my God, would you send that to me? No, he said, I can't. I said, you can't? He said, no, I have it in confidence. It's not even, it's been sent to peer review yet. It hasn't been sent to the journal. And I couldn't possibly send it to you. And I said, okay, mine's the same way. But would you contact them and ask if it would be okay for you to send them a copy of my paper to see what they think about it, and also if they could give you permission for you to send me theirs. And that's what happened. And a few days later, McKay called me and told me that they had said okay. So he sent me their paper, and they had found almost identical kinds of things. Not the same thing, but the same type of things, cyanobacteria, in the meteorite that they were looking at. And they were looking at Murchison meteorite as well. And so here we had 2 independent results from completely different continents. And so I gave this paper at the first SPIE meeting that we had on the subject. And I had invited a number of scientists. And one of the things that needs to be known is we're now talking about 1996. In 1996, America and Russia were very friendly. America and Russia were 2 very, very strongly cooperating nations.
It's a different world back then, yeah.
In fact, I rode on several airplanes with a NASA administrator going to Moscow, and we
Which administrator?
Was it Golden? I think it was maybe Dan Golden. Dan Golden. And I think one of the others too, but at any rate, we had in Moscow, in what was called was before the Hotel Renaissance became there, by the Olympic Stadium, the Pinta, the Hotel Pinta. When I got there, I found out that NASA Marshall had the 6th floor of the Pinta Hotel. It belonged to NASA scientists. I mean, they had booked it, and in fact, NASA had installed communication links so that my phone by the side of my bed in my hotel room in Moscow, I could pick it up and dial a local phone number, and Miriam could answer the telephone. And she could call me by dialing my Huntsville phone number by the side of my bed in Moscow.
Man, that's cool.
So so the relationship was very close. And in fact, one of the first programs that I was involved in was called the Joint U.S.-Russia Research in Space Science, the JURIS program, sponsored by NASA. And that was a way of sending money to the Russians. I did 3 proposals, 2 of them were approved, and I got a small bit of the money, but most of the money went to academician Mikhail Ivanov, and part of it went to academician Rozanov, who was a corresponding member at that time of the Russian Academy of Sciences, to continue their research. This was a way of NASA sending money to Russian scientists, to support Russian science.
Let's try to sum up your work with the Russians here. Approximately how many papers since 1997 did you publish with them?
I could not guess. Many.
10?
No.
20?
20, 30,
30?
40, I don't know.
Dozens.
Dozens, yes,
Okay.
dozens.
So they do good work. They recognized you
Yeah,
as doing great work. You've been
Yeah.
there how many times?
Oh, I've been to Russia many times. I started in 1997, and after that I went back to Russia almost at least once or twice a year. And got to know and become very good friends with many of the academicians and the scientists, and then the astrobiology group was formed at the Joint Institute of Nuclear Research in Dubna. We got a scanning electron microscope there, and I started working. Alexei Rozanov established that. I started working with Alexei in the Joint Institute of Nuclear Research.
So for anyone who doubts this Russian team of scientists as far as their credentials and how qualified they are to be looking at microfossils and meteorites, what would you say?
Well, I would say they don't know what they're talking about. All they got to do is look up, for example, Yuri Oganessian. Academician Yuri Oganessian was the one who synthesized the last 4 elements of the periodic table of the elements. Element number 118 is named Oganesson, after Yuri Oganessian.
Okay.
He is the only human being alive with a chemical element named for him.
You're saying that's how serious the Russians are.
Oh my God, yes.
They got elements named after
They've
them.
got elements named. In fact, they've synthesized most of the upper level of the periodic table of the elements.
Okay, so they're not amateurs.
They're absolute. And of course, they were doing this research in collaboration with people like Lawrence Livermore National Laboratory, Oak Ridge National Laboratory.
Well respected.
Yes.
Okay, so you have George Klaus, Naj, okay, all the way up until your work with the Russians here. Meanwhile, we also have your colleague, Professor Chandra Wickramasinghe, who worked extensively throughout the 20th century with Sir Fred Hoyle,
Yes.
studying cosmic dust, interstellar space,
Comets.
Okay,
yes,
so
and Panspermia.
Panspermia. He's a
One of the pioneers with Fred Hoyle. And
many people consider them to be the pioneers of panspermia, and he essentially just trying to distill his research down here. He's published dozens of papers on basically the discovery of organic material in space. Do I have that right?
yes, but not dozens. I would say probably more like 100. I mean, a lot of papers.
Tell us about your work with Professor Wickramasinghe.
Well, I started working with Chandra in 1984, 1985, when we started working on this paper on interstellar dust and diatoms. And Chandra was one of the co-authors of this paper that I wrote with the late Sir Fred Hoyle. And that paper shows this remarkable agreement between the spectral properties of interstellar dust in the direction of the Trapezium Nebula and the galactic center black hole GCIRS 7, and a mixture of diatoms and bacteria. The paper clearly shows that interstellar dust is not made of inorganic silicates, but rather polymeric silica like you find in diatom shells, like you find in radiolaria, like you find in many of the kinds of life forms that build these silica shells by putting down a molecule of silicon dioxide with water of hydration, one molecule at a time, to build these intricate structures that are very reproducible, very perfect. And that's the results of that indicate that biology is a universal phenomenon.
You and Professor Wickramasinghe, among a few others, did some work with what is known as the Polonnaruwa meteorite, okay, which fell in Sri Lanka in 2012. Now, there have been a couple of papers published on the Polonnaruwa meteorite as of a decade ago, but even today, 2024, you guys are still working on this thing, aren't you?
Oh, there have been many more than 2 papers published. Many papers.
I try my best to keep up with you guys. You guys keep going and going. You know how many people publish research?
Yeah.
But you're in the lab today. You were in the lab this morning.
I was in the lab
He showed
this
up
morning.
late to this interview because he was in the lab doing work.
Yeah, looking at Polonarua under the scanning electron microscope and finding spectacular things.
Spectacular thing.
Magnificent diatoms. Just a few days ago, we found tube-dwelling diatoms in the Polonarua meteorite. And in fact, the tube-dwelling diatoms that we saw are marine diatoms. And they're from oceans. They're found, in fact, many of them are commonly found in sea ice environments, in polar regimes. The most abundant tube-dwelling diatoms are in the polar regions. And these little diatoms build tubes that they live in, and they build those tubes by excreting exopolysaccharide, and then they move around within those tubes. And in fact, they were first studied way back in the late 1700s, and they were named Schizonema and Berkelia. And
we've known about these kind of diatoms since
we've known about those kinds of diatoms since the very beginnings of diatom research. And in fact, my life goes in circles. When I was working in Antwerp, I mentioned I mentioned my visit to Antwerp, Belgium. I don't know if I mentioned that I was invited to do the study of the Henri van Herk Museum. But in 1974, I was working on a book to be published by Academic Press with Frederick I. Ordway III. And this book was going to be called The Unseen World, the Microcosm and the Macrocosm. And at that time, I was looking for information on how telescopes and microscopes had expanded human vision and allowed us to see unseen things in the world of the very small and the world of the very great and grand. And so I told my friend in London, Holly Martinlew, what I was doing. And she said, let's go to Belgium. John's there, her husband, and he can possibly help us find what you want. So we went to Brussels and got together with John, and I told him what I was doing. And the next day he called and he said, we got to go between Brussels and Antwerp because there's a gentleman there that knows everything about the science museums of Europe. I thought, yeah, that's nice. So later that day, we drove there, and when we got there, rang the bell on this beautiful little place out in the middle of nowhere. The door answered, and a 1930s vintage French maid answered the door with the typical costume you see in the old movies, and a small hat and short skirt and all of this. And she invited us in because he had already called earlier, and brought us in for tea and scones, waiting for the professor to come down from his study. And I told him what I was doing, and he said, yes, I can help you. He said, I did the inventory of the scientific museums of Europe, and let us go upstairs and I will show you what you need to know. And then we went upstairs, and he pulled off this big shelf about scientific museums of Europe, and I noticed his name was on the cover. And then he starts telling me where there were big telescope by Herschel in London, and then he mentions that there were 3 of the Antoni van Leeuwenhoek original microscopes at the Royal Zoological Society of Antwerp. And then he explained that they were part of the Henri van Herk Museum, and then he starts telling me that Henri van Herk worked with diatoms. Had I heard of diatoms?
Bing, 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 magic word.
I had heard about diatoms by then, and I had Van Herk's book, which I had used extensively. And so the next day, we headed to the Royal Society of Zoology of Antwerp, and there were the 3 original Leeuwenhoeks. I photographed them through the glass, and then we went out and were looking at the okapi, and someone came out and says, Dr. Vandenberg wants to see you. I said, Dr. Vandenberg. I said, who is that? Well, he's the director of the Royal Society. Okay. Yes, I would be delighted to see him. So we went in and we talked, and when I told him what I was doing, he wanted to know if I had actually seen the Leeuwenhoek microscopes. I said, yes, I took photographs. He called somebody over, and about 15 minutes later, the guy hands him an original Antoni van Leeuwenhoek microscope. And he took it in his hands and handed it to me. I mean, here I am holding an instrument built by Leeuwenhoek himself in my hands. I was absolutely astonished, as you can imagine. And then I said to...
You had to give it back.
Well, yeah, unfortunately I had to give it back, but I didn't give it back immediately because I said, do you mind if I look at something with this? He says, do you know how to use it? I said, I've had a copy I bought in Utrecht at the museum 3 years ago. Yes, I know how to use it. Oh, he said, what would you like to look at? I said, a diatom. Well, do you need anything? I said, I need a microscope slide. I'd like an artist brush. I'd like some Scotch tape and a pair of scissors. And he sent the guy off to get my request. And I'm sure the guy thought I was kind of strange, but he brought it back, and I clipped one of the bristles from the artist brush and taped it to the end. And then I reached in my pocket and pulled out a beautiful assemblage of dried, cleaned Antarctic diatoms and dumped a few of them out on the microscope slide, and reached in and found one of the big triceratium, about 150 micron triangular diatom, and picked it up with the eyelash or the hog's eyelash on the, which is what the artist brush was made out of, on the end of the brush, and put it on the needle that was where you mount things for the Leeuwenhoek microscope, and then adjusted it until it was in front of the lens and focused it, and it was like I was looking at a diatom with a compound microscope. It was spectacular.
You just happen to have diatoms in your pocket?
I have diatoms all the time. I have diatoms with me right now.
Oh, stop it.
Well,
oh, here we go.
right there. This is Polonarua meteorite containing diatoms, and this is also Polonarua.
You got the Polonarua meteorite there?
Right there.
You got a Polonarua meteorite in your pocket?
Yeah, this is on a stub.
Okay, hang on a second.
Yeah.
Can I...
Well, actually, I've got bigger pieces in my car. If you'd like to see what one looks like, I can allow you to take a film of it, and I can show you the astonishing density of it. So I had these diatoms, and then I took a look at it, was shocked at how beautiful it was, and then I handed it to Vandenberg, and Walter Vandenberg looked at it, and he said, you know, we have had this collection here since 1907. It has been a part of the Royal Society of Antwerp since that time, when Henri van Herk died and it was willed to the city of Antwerp. And I have never before had a chance to see anything with this Leeuwenhoek microscope. So, and they took it back, unfortunately. They wouldn't let me have it. But he wound up inviting me to come and inventory the Henri van Herk diatom collection. And I spent several years going back and forth to Antwerp and inventorying that collection. And in that collection, I studied some of the Gruno material that I discovered, and it contained tube-dwelling diatoms.
Okay, all right.
And that's what we were looking at the other day, was tube-dwelling diatoms from Gruno's material. So I keep going circles.
God.
I keep going in full circles.
My God. All right. Okay. Last thing about Polonarua, and we're gonna segue into what your skeptics critique you about mostly. Okay. First of all, with Polonarua or any of these meteorites, how do you know it came from the sky if you didn't see it fall?
You don't have to see it fall. You can tell that it came from the sky by scientific analysis. For example, the carbonaceous chondrites, like Orgay and Murchison and Murray and these various other Ivuna, they have done analysis of the elements. And in fact, we did neutron activation analysis of the elements of many of these meteorites, as well as Polonarua. And the element composition, the relative abundance of the refractory elements, things like iron and nickel and carbon and calcium and magnesium. You can't say anything about the gases, the hydrogen and helium and so forth. But these other elements, you can look at their relative abundances, and you find that their relative abundances are not at all like the abundance of these elements in the crust of the Earth. They're like the abundances of these elements in the photosphere of the sun. So that proves that they are actually part of what is called the protonebula condensate that formed when our solar system was formed. These meteorites, like Orgay and Murchison, contain nanodiamonds, 6 billion years old. The nanodiamonds and silicon dioxide, corundums, and so forth, particles, are older than the planet Earth. Now, when you've got particles in the meteorite that are older than the planet Earth, you know it isn't an earthly rock. The Polonarua stones are even more bizarre. They have incredibly low densities. Below 1, they'll float on water.
The stones will float on water.
Stones will float on water. There are only 2 stones on Earth that will do that. Pumice from volcanoes and diatomite are the only 2 stones that will float on water, and Polonarua. And just recently, they discovered that the Gargoyle Saxon boulder on the asteroid is also of a density very similar to the Polonarua stones. So these stones may be related to asteroidal boulders. I don't know. They're a great mystery because of many reasons, but the biology that they contain is glorious. It's absolutely amazing.
Okay. I go on the internet, I find some guy, I'm looking to pick a fight. I'm like, yes, in fact, there are microfossils in meteorites. I got a guy here in Alabama who's studied them his entire career. He knows everything about them. He knows a whole lot more about them than most other people. And here's what they'll respond with. It's just contaminated.
Yeah. Mm-hmm. Well, first of all, something you said there was wrong. I don't know everything about them. I wish to heck I did. There are a bunch of things that we've found that I haven't a clue what I'm looking at and that are totally bizarre. But the point is, I have literally, since 1996, now what is that? 2006, 2016.
28 years ago?
28 years. For 28 years, I have devoted an enormous amount of time and research to these meteorites, and specifically to the microbiology of the meteorites. So when someone says, well, I don't believe it, well, that's fine. Do you believe the Earth is round?
They'll say it's contaminated.
Oh, well,
Meaning an Earth creature
crawled in
as soon as you put it under the microscope.
Yeah. Well,
and your response is?
The response is, I can prove they're not contamination because of several things. These meteorites...
Now, first of all, before you continue, you said prove.
Prove.
This means something.
This means something.
This is
I can
prove.
Prove.
To prove something means you have more than just evidence.
You have solid evidence. You have solid evidence from more than one experiment.
So I'm going to write prove in all capital letters with an underline underneath.
With an underline.
Okay, you can prove what?
Well, let's first go back to the question of proof. After David McKay's discovery, a lot of people started criticizing David McKay by saying, well, that's an extraordinary claim. And everybody knows extraordinary claims require extraordinary proof. I'm sure you've heard that. That's common. In fact, for almost a year, I said the same thing myself.
They'll say evidence, extraordinary evidence.
Extraordinary, well, in fact, they sometimes said extraordinary evidence. They sometimes said extraordinary proof.
Okay, all right.
But what is proof? If I tell you triangle A is congruent to triangle B, if you've studied the geometry of Euclid, which goes back a few hundred years, the Way you do that is you show that the dimensions of the three sides are the same, or side, side, side equals side, 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 or one side and the angle between and the other side is equal to one side and the angle between and the other side of the other triangle. And when you get that done, you write QED, quod erat demonstratum. That is proof. All we need to demonstrate, it is done, full stop, quit. You don't have to do anything else.
Okay, they say it's contaminated. You say it's not because
Okay,
why?
Because of several reasons. One, all living things contain this same suite of elements that I told you about: carbon, hydrogen, oxygen, and nitrogen. And the relative abundances are very well understood. In fact, when I look at woolly mammoth hair, 32,000 years old, I see about 11% nitrogen. When I look at the fossils in these meteorites, on a very few occasions I can detect up to a couple of percent, in one case 3% nitrogen, but almost always you can't see nitrogen at all.
If it has no nitrogen,
Then that means it is ancient,
how?
because nitrogen goes...
By how old?
Well,
Ancient meaning how old?
ancient meaning 100,000, few 100,000 years, millions of years to billions of years. When the nitrogen's gone, you can't tell whether it was a billion years that it died or a few 100,000 years ago that it died. Although I have actually seen some nitrogen in some fossils that are older than a few 100,000 years, but it's very strong in woolly mammoth hairs. And there are no modern woolly mammoths running around that could give rise to contaminated hair from modern mammoths. So the point is, nitrogen is the most definitive elemental evidence. The presence or absence of nitrogen is is very definitive elemental evidence of modern biology or ancient biology. But even more important than that, more important is the fact that there are enormous numbers of scientists that have studied meteorites, carbonaceous meteorites. And they find amino acids in the carbonaceous meteorites. They find amino acids in the samples returned from asteroid Bennu and asteroid Ryugu. And those amino acids that they find, in the case of Orge, they find 8 amino acids. In the case of Murchison, 12. The 12 protein, and I should say they find many more amino acids than that, but 12 of the protein amino acids, which are the ones that are important for biology. The proteinogenic, they're called. They're the ones that make proteins. Well, the point is, if I put in a single bacterium in my rock, allow a tiny gnat to fly over and lay some eggs on the rock, or allow a diatom to crawl into it that's alive, if I put in a single living microorganism and then do the kind of analysis that these people do, looking at very sophisticated techniques, looking for amino acids and nucleobases, you could certainly find all 20 protein amino acids and all 5 nucleobases. You've got to have all 5 nucleobases, the adenine, thymine, guanine, and cytosine, and uracil. The adenine pairs with the thymine, the guanine pairs with the cytosine, and that's how the DNA molecule preserves the genetic code, the Gattaca, G-A-T-A-C-A. So that's how the genetic code is written, is with guanine, adenine, thymine, and cytosine. Without the genetic code, you don't have biology, all right? But the fact that guanine always pairs with cytosine in every DNA molecule, you should find exactly the same amount of cytosine in the meteorite as guanine, and you don't. Cytosine is almost always below the level of detectability. Guanine is detectable. So the point is, and you can find uracil, but the thymine is almost never found, and the cytosine is almost never found. If I contaminate my meteorite with a living organism, and I do it since it fell which of course the oldest one I've studied in carbonaceous chondrites is 1806, which is recent, then I should have, and everybody that looks at it should find the same amount of guanine as there is cytosine, unless everybody's meteorite is pristine and every one of the meteorites that I get happens to be contaminated by modern biology. I'm just lucky that way. So the point is, these studies directly of the fossils themselves prove they're ancient, show undeniably that these fossils are ancient. And the absence of these nucleobases that decay over geological time periods show that the biology that was there had to have died a long time ago. The other point is homochirality. When you look at the carbonaceous meteorites, the amino acids that you find, many of them proteinogenic or racemic, equal quantities of D and L. But some of the amino acids have a very, very significant increase in the L amino acid, which is much more than you can make by non-biological processes. So that says that these L amino acids that you find that contain a significant excess, they were from living organisms that died hundreds of thousands to millions of years ago, and then over a period of time, the amino acids in the meteorite started to flip from L to D, started doing this flipping from one type to another, which happens, and that is the basis for amino acid geochronology that was pioneered by Jeffrey Beta and John Carriage, and they can use the relative abundance of L and D amino acids to date strata, to date sediments, farther back than you can do with carbon-12. So amino acid geochronology is a well-accepted science, and the absence of pure L amino acids in the meteorites, the presence of an excess of some of them far greater than you can get by abiotic processes says, folks, there was biology alive here once, but it died long ago. Now, how long was long ago? It sure as the heck wasn't 150 years. It sure wasn't 200 years. It may have been 100,000 years. It may have been 100 million years or a billion years. I can't answer that question, but it's ancient.
Okay. I hate that I have to ask you this next question, especially since you gave me that wonderful explanation. But for the people out there who still aren't convinced, okay, that you know what you're doing, can you briefly just describe your sterilization process?
Yes. What we do before we work with the meteorites is we typically use an aluminum pan that is for scanning electron microscopy purposes. And I typically take a propane torch. In fact, the ones I like are the ones that people use to light cigars. Not a cigarette lighter, but a propane torch. You flick that and a blue-white flame comes out. And when you put the sample in, before you put the sample into the tray, I flash the bottom of the tray, which means if there's any modern biology there, if there's a bacteria that happened to be there, although we use things coming out of sealed containers, but any biology that happened to be there is going to be vaporized. First of all, incinerated and then vaporized. And when I use tweezers, I typically flame sterilize them by heating them to the glow from red to yellow to sometimes white at the tips where I'm going to touch the meteorite. And the other point is we fracture the meteorite and look at interior surfaces, so we don't look at the outer surface. I try to avoid outer surface in all cases and stick it onto the microscope substrate and then put it directly into the microscope. Now, the point is that when we see the kind of assemblages of biology, I can assure you there is no possibility. I mean, I've looked at rocks, I've looked for diatoms all over the world, and I'm seeing things here that I have never seen before, where you have enormous assemblages of diatoms in close proximity to strange crystals, and also, where you see where one diatom has undergone many cell divisions, one after the other, after the other, after the other. This is an amazing set of images that I've got.
What I want to talk about next is extremophiles and your work. I watched a video of yours where you maybe went to, was it the North Pole, where you reanimated frozen microbes from the permafrost?
It was in the Kolyma lowlands of far northeast Siberia. Not the North Pole. I've never been to the North Pole. I've been to the South Pole.
It's up there somewhere, right?
It's very, very high in latitude. In 1996, David McKay announced the discovery of possible nanofossils in the Mars meteorite. I thought, this is crazy. Everybody knows there are fossils in meteorites. I knew it. I thought everybody in the world knew it. In fact, I had co-authored a paper with Fred Hoyle and with Miriam that was published in Earth, Moon, and Planets in 1986. And in that paper, we talked about extremophiles, we talked about diatoms in ice, and how diatoms could live and take care of themselves during the polar winters, when in Antarctica and in the North Pole and South Pole regimes, when it gets nighttime, it gets serious about it. So when the diatoms experienced night, they stopped carrying out photosynthesis and started eating. So they went from photoautotrophs to organotrophs. Well, that had resulted in my work in knowing about these various aspects of what ultimately came to be known as astrobiology. And when David McKay made this announcement, as I said, I was shocked. I thought everybody knew there were fossils in meteorites because Klaus and Nagy had shown that in 1962. What happened was I went to the executive director of SPIE, where I was chairing a series of conferences on X-ray optics, and told him next year we need to have a conference on instruments, methods, and missions for the investigations of extraterrestrial microorganisms. He said, why would SPIE, since we do optics, why would we be interested in such a thing? I said, I believe they're probably going to be interested in developing spectrometers and telescopes and rovers to search for life on Mars, to search for life on Europa or Enceladus. And this might involve things that might include optics. And they said, yes, I see what you're saying. Well, would you be able to get someone to chair such a conference? And I said, yes. He said, would you be able to do it? I said, I would be delighted to. So I agreed to chair the conference, the first conference on extraterrestrial life, on microorganisms in meteorites and other areas. And as soon as I had agreed to do that, and David McKay, his results were starting to be very, very greatly exciting to many groups around the world. What happened was NASA decided to form the astrobiology program and to set up the virtual astrobiology institutes. Well, I then thought, wait a minute, do I really know that there are microfossils in meteorites? And I realized I had read about this, but I didn't know for sure. And at that point in time, we had here at Marshall an environmental scanning electron microscope. And the interesting thing is now David McKay's work was coming into controversy. Lots of people arguing that what he was finding there was not biology at all, but was coding artifacts or were things that were too small for life. Well, I decided that we could use the environmental scanning electron microscope and get around some of those problems, because that kind of microscope uses water vapor in the chamber to carry away the charge, so you can look at things that have never been coated with gold or carbon. So you can't have coating artifacts if you don't coat. And I ordered from a famous, very reputable meteorite dealer a 1 gram sample of the Murchison meteorite, and I started breaking it open and taking photographs, and immediately found fossils in the meteorite. So we can come back to that later, but what that resulted in was me organizing this first meeting in San Diego, and I invited Alexei Rozanov, who was working in a similar area, and the brilliant microbiologist Mikhail Ivanov, the director of the Microbiological Institute of the Russian Academy of Sciences, and with several other famous Russian scientists who all came to the meeting. And at the meeting, David Gilachinsky invited me to come to join their expedition to the far northeast of Siberia to look for life in one of the most extreme and hostile environments possible. And that was, the purpose was to search for life in cryopegs.
What's that?
Cryopegs, CRYOPEG.
Cryopegs.
Yeah. I think
it's a cryopeg.
It's also pronounced cryopeg. But it's spelled like cryopeg.
Okay. What's that?
And what happens is, under the permafrost, when you go deep down in the permafrost, what has happened is the salts leach out, and so you get a hypersaline brine beneath the upper layers of permafrost, and it remains liquid at temperatures as far down as 20 below zero. So we're
saying really salty water.
Oh, very salty water.
In the frozen soil.
Underneath frozen soil, and temperatures far below zero.
Okay.
And the purpose was to go to northeast Siberia, to the Kolyma lowlands, and to drill in the permafrost to try to encounter a cryopeg. I went to my boss and told him that I had been invited by the Russians to go to far north Siberia. Would he approve my travel? And he looked at me and he said, "Sure, if I can buy you a one-way ticket." I said, "Okay," and I ran out of his office. He'd approved it. I didn't think they'd let him buy me a one-way ticket after all. So I was delighted. And so I went, starting making preparations to go to North Siberia. I then turned in my travel orders to go to far northeast Siberia, and for about 6 weeks. To my great surprise, NASA approved this, and of course the whole area of astrobiology was very exciting at that point in time. And so they called me back and said, "We can't get you a plane ticket to Chukchi and to Tiksi in northeast Siberia." So I called David. I said, "I don't understand. They say they can't buy me a plane ticket to Cherski," which was my final destination. And he said, "Of course not." I said, "What do you mean?" He says, "We have to buy the plane ticket here. You'll have to bring rubles. We'll buy your plane ticket in Moscow." And he said, "And then you have to bring money because we will buy your plane ticket from Tiksi to Cherski in Tiksi." So I got there and I paid cash for my ticket from Moscow to Tiksi. And when I asked him why I couldn't buy it all the way through, he said, "But if we did that, how would the people in Tiksi get their money?" I thought, yeah, I understand that. It wouldn't be possible. They had no banking system. I mean, then this town of Tiksi had been highly classified for many, many years. So we flew there. In fact, when I was preparing to go, I realized that where I was going in North Siberia, I was actually considerably further away from Moscow than Huntsville was. Because Siberia is big. It is a very, very big place. So we flew to Tiksi, and I got new tickets. I went in to buy some souvenirs, and most interesting because you picked out the little piece of paper with what you wanted to buy, and then the girl would go over to an abacus and click away and tell you how much money you owed, and then you paid them, and they would go collect your merchandise for you.
Abacus?
An abacus. That was the way they calculated. It was the only time in my life I've seen people actually using an abacus for real commerce.
In the 90s?
That was in 1998. They were using an abacus. And so then we landed in Chersky, and we spent about a week in Chersky talking with the guy that was doing Pleistocene Park. His intent was to build a replica of the Pleistocene, and he was bringing in all sorts of exotic animals, muskox and so forth. And then we ultimately came time to fly to northeast Siberia, and several things were very interesting there. They flew in a big helicopter, and we were loading all of our gear into this Ilyushin helicopter, and David Gilachinski was stuffing big knives into steel drill tubes. And I said, David, I said, what are you doing? He said, I don't want them to know I have these big knives. And I said, why? He said, I don't think they would allow us on the helicopter. I said, David, if we tried to hijack the helicopter, where could we fly to? There was nothing in the range except Siberia. So, yes, I know, but he says it's not permitted. So we smuggled the knives into Siberia in the steel drill tubes. And when we were getting ready to leave, I was standing there looking at this huge helicopter, and the right front tire was flat. And I told David, I said, our helicopter's got a flat tire. And all of a sudden I realized the captain was standing right behind us, a big tall guy, and he walked around us and kind of in a huff went out to the helicopter. And I thought, oh my gosh, at least he knows about it. He'll fix it. That's good. And he kicked the tire twice, and then he walked back, walked up to me, stared down like he was looking at a child, and he says, he's helicopter, no need wheels. So we flew with a flat tire. No need wheels.
Man knows his machine.
Oh, incredible. We had drums of diesel fuel. We had people sitting on the drums of diesel fuel. I was sitting with my feet dangling out of the helicopter. And people, the whole group of about 14 of us, including a Cherokee Cooker woman and her daughter, the entire team went up on this big helicopter with enormous amount of gear, including boats. And when we landed there in North Siberia, this was from Chersky into Lake Yakutsk. When we landed to the Yakutsk area, the helicopter was going to keep the props running, and we had to throw all of the gear out of this huge helicopter, and then jump out and hit the ground in the very wet tundra. And because as soon as we got everything out and we were out, it took off, and there was this colossal downdraft. And we were cautioned, you don't stand up, you wait until he's gone. And the reason they did that was because they didn't want to take a chance on killing the engine and not being able to start it. So they had.
Was it cold up there?
It was not cold that day. In fact, it was quite pleasant. I would say it was about 50, 55 degrees Fahrenheit when we first arrived in the area of Lake Yakutsk, and it stayed in the 60s to 70s. So it was a nice autumn day. We arrived in early August, and we stayed there and it was very pleasant. We were drilling in the permafrost every day, and we had autumn, beautiful. Well, actually, we had summer. We didn't realize it was summer, but it was summer, because then on the 15th of August, we had autumn because the temperature dropped to about 40 degrees Fahrenheit. And then that was, I recall, on the 15th of August. And then on the 16th, autumn was over and we went into winter. Because the temperature dropped to 31, 32 degrees with rain, around a 40-mile-an-hour wind. The raindrops would sting when they hit you, and my tent was popping back and forth, and every time it would pop, there would be rain falling on me, and I was incredibly cold. And as the time went on, about 3 o'clock in the morning, I realized that I wanted to use the facilities, and I got up to leave the tent and discovered, to my great surprise, that it had stopped raining. But the only reason it stopped raining was because it started snowing.
You go through all this trouble to go up to Siberia, okay, and you're looking to study the microbes that you can pull out of the permafrost.
Yes.
Okay, and long story short, microbes were frozen thousands, perhaps millions of years ago, and there's a process of, well, you tell me what happened next.
Well, we have been studying several things. The ones in the cryopegs were, what we were wanting to see was living things moving and swimming and replicating and metabolizing at extremely low temperatures. So that was the purpose of searching for microorganisms inside of the liquid water, the hypersaline water. But we had also taken samples of the permafrost, and microorganisms live in the permafrost, remain alive for very, very great periods of time. Before I went to North Siberia, I had also made a trip to the permafrost of the Fox Tunnel of Alaska. And we had discovered bacteria inside a frozen pond, a thermokarst pond, that was seen in cross-section, and the bottom of the pond was a nice golden brown when I encountered it inside the Fox Tunnel. And I took samples of the ice because I was sure that this was diatoms in the bottom of this pond. And I immediately called a friend, a professor at the University of Fairbanks, and asked her if I could come over and use her microscope to take a look at the diatoms that I had collected, because I couldn't wait until I got back to Huntsville. And she invited me. So I went over with some of these samples of ice that I had collected in Alaska in the Fox Permafrost Tunnel, and put a drop under the microscope and looked in, and there were no diatoms. And I went to higher magnification, and there were no diatoms. And then I went to oil immersion at about 1000x, and there were bacteria, and they were swimming very, very rapidly. The ice had melted, and these bacteria had come out, and they were rapidly swimming, even though they came out of the ice of the Fox Permafrost Tunnel. Well, I brought this back to Huntsville, and Dr. Pikuta, my colleague from Russia who had come to work, in fact, she still lives here in Huntsville, and she's been working with me ever since 1997. And Dr. Elena Pikuta did the isolation, and we were then able to do a complete analysis and description, and we published Carnobacterium pleistocenium, which was the first living Pleistocene organism known on Earth. And after that paper was published, I had a lot of calls. In fact, I got a call from a reporter from the New York Times, and he wanted to talk about it, and I told him the details. And he says, how do you know this wasn't contamination? And I said, well, because of the way I collected it. Well, he said, we've spoken with Professor Willerslev I think he was at Cambridge. And he tells us this is not possible because DNA cannot remain intact for 40,000 years. And he says this is modern contamination. And I said, well, I don't understand why he would say that. I said, and he thinks that this is contaminant. He said, yes. And I said, well, I don't understand. Why would he say that? Well, Professor Willerslev tells me that this Fox tunnel has a big air conditioning unit in front that you have to go through in order to get into the tunnel. I said, yes. I said, that's correct. He's been there? No, but he tells me he knows about it. I said, oh, okay. Well, in fact, the way it works is it's run by the Cold Regions Research and Engineering Laboratory, CREL, part of the United States Army, in Fox, Alaska. And this tunnel was built when they were getting ready to build the Alaska pipeline. And they were trying to develop equipment that could drill through the permafrost. And that was their test bed, was the drilling into a mountain through permafrost. And so they built this whole laboratory to study the nature and characteristics of permafrost. And so when you go in, you have to go with someone. They unlock the outer door and you go into an airlock kind of thing. And the outer door is closed and you get suited up. And then you have to sit there and wait until the air conditioning system pumps the region you're in down to below -4°C. And then it allows you to open the inner door to walk into the tunnel itself. And the reason is to keep this perennially frozen and not allow it to ever get above -4. And of course, much of the time it's significantly below -4, but at -4, nothing will melt. So he says that Professor Willerslev says that he thinks that at some point in time the air conditioning system had failed and the permafrost pond you were examining had thawed out and modern bacteria had gotten in because people go in and out of the tunnel to do research. And I said, yes, that's correct. People go in and out of the tunnel, but I said that theory is simply not valid. And he said, well, how can you be sure that the air conditioning system hadn't failed and that the tunnel had been allowed to thaw out? And I said, well, because we were examining a section through a Pleistocene pond, and the bottom of the pond was about 4 foot above the bottom of the tunnel, and the top about 10 feet above the top of the bottom of the tunnel. And it was a vertical wall of ice. And I said, if the temperature had ever gotten above freezing, the wall of ice would have melted, and the liquid water would have been an ice rink on the floor of the tunnel. And I suggest Professor Willerslev's theory just simply doesn't hold water. He said, that's a good explanation. About a year after that, I got a paper to review that was written by Willerslev. I was saying that he had been able to keep DNA intact for well over 100,000 years. And when I reviewed the paper, I said I was delighted to see that he had realized that DNA could remain intact for vast periods of time. And in fact, I have in my freezer right here in Huntsville pieces of Beacon Valley ice, still frozen, that contain not diatoms, but bacteria, living bacteria. I haven't found any diatoms in the Beacon Valley, but we found all sorts of bacteria that are alive that were frozen in the Beacon Valley Glacier of Antarctica 8.3 million years ago. Now, one might say
8.3 million
8.3 million. You might say, how do you know it's 8.3 million? Well, the same logic. In the Beacon Valley Glacier in the Miocene, there was a volcanic eruption and big boulders were thrown out. and they landed on the Beacon Valley Glacier, some of these as big as this house. And those boulders are still sitting on the top of the glacier. Now, if that glacier had ever thawed, the boulders would have fallen through the water and been on the bottom. So that proves that the glacier has remained frozen for 8.3 million years. And so from taking interior material from the inner part of the glacier, just like I did in the Whistler Ice Cave in Canada, or with the Ancient Aliens program, or with the BBC with Brian Cox in Iceland, we're looking at ancient ice that the outer region is removed by chopping it away, and then the inner ice contains the indigenous bacteria and other microorganisms that we can extract and show that as soon as the ice melts, they come out and they start swimming around.
So they were frozen.
Frozen solid.
The ice melts.
Yep.
Essentially, you're applying water to it because the ice is melting, and then they are reanimated. They come alive again.
They don't actually come alive again. I'm convinced they were always alive. But they start swimming.
Dormant state.
They were probably carrying out very, very slow metabolism.
8.3 million years.
Yeah, 8.3 million years. Or they may have been in a totally dormant state. I have no way of knowing. And in fact, it could be that some of both is going on. So the point is the exact nature of how these organisms are able to remain alive for vast periods of time. And I must say 8.3 is just trivial. Just trivial. Because actually, we did a paper on Mississippian sylvite in which we cultured bacteria, Dr. Pakuta and I, and that was 325 million year old microorganisms. And one of the saddest stories, 325, one of the saddest stories of all is the story of Professor Dombrowski from Justice Leibniz University. And Professor Dombrowski, back in 1962, attended this meeting at the New York Academy of Science, and he talked about bacteria in ancient salt deposits. And he had taken ancient salts. He had taken Pleistocene salt and Miocene salt and Devonian salt and Cambrian salt. And he had taken these salt crystals, some from Irkutsk, Russia, and he would cleave them and make thin pieces of salt and look at them under the microscope and see bacteria inside the salt, and then he was able to culture the bacteria. One of the preeminent microbiologists of Europe. And he lost his job because of the paper he published. And the reason was what he had said was obviously absurd, obviously couldn't possibly be right. And in fact, it was Sir Fred Hoyle that told me that Dombrowski had lost his tenured position because of that atrocious paper that he had written and published in the scientific literature. In fact, George Klaus, the one that worked on what was called organized elements in meteorites, when I mentioned the term to him, he slammed the phone down. When I told Sam Van Lanningham about what had happened, he said, "Of course, I thought you knew." And I said, "Thought I knew what?" "Oh, George Klaus is convinced that their discovery of microfossils in the Orgay meteorite totally destroyed his life." So I have to say, I'm fully aware of the fact that there are people that are saying, we don't accept any of this nonsense. It's total hogwash. There can't possibly be microorganisms in meteorites. And in fact, when my paper was published in 2011,
we'll talk about that.
There was a guy at headquarters that said, we know this can't be possible because we know extraterrestrial life doesn't exist.
We're going to talk more about that. Tell me about your time down in Antarctica.
Antarctica, one of my favorite places on Earth, probably my favorite place on Earth. I organized the expedition, the International 2000 Astrobiology Antarctica expedition, after I came back from Siberia, because we were interested in doing two things. We were interested in studying microorganisms that live in ice, the coldest regime, and also meteorites. And Paul Sapira of the Planetary Studies Foundation was interested in going. So we put together the expedition to go to Antarctica. Jim Pritzker provided the dominant portion of the funding for it. And the arrangements were then made. I had some members of my team, and I also invited Owen Garriott, who was working with me at the time on microbial extremophiles, and Jim Lovell, Commander Lovell from Apollo 8 and Apollo 15 missions that Paul Sapira knew very well. And he had never been to Antarctica, so he was very much interested in going and participating in the expedition. The Fox TV team, Amanda Onion and others from Fox News, were interested in covering the expedition, so they sent Adam Petlin, their photographer, and Amanda Onion to do reporting on the expedition. And we made the plans and decided that what we would do is we would fly into Antarctica, into the Patriot Hills, because what we wanted to do was first go to the Patriot Hills to acclimatize a bit, and then fly to the Teal Mountains. The reason we wanted to go to the Teals was because we wanted to search for meteorites. One of the interesting things about Antarctica is the wind always blows, and the wind is almost always blowing from the South Pole toward the coast. And because the coast is at sea level and the South Pole is over 11,000 feet elevation. So at the South Pole, you're on the top of a very tall mountain that goes downward in every direction. And so basically, these winds typically flow from the south to the north, just about anywhere you are in Antarctica. And if you encounter a mountain range like the Transantarctic Mountains, the wind comes from the south, hits the mountains, goes up over the top of the mountains, and then down the other side. And as it is lifted up by the mountain range, it goes into colder regimes, and the moisture falls out as snow and sleet. So on the other side, when it comes down, the wind is typically what's called a katabatic wind, that is a very dry air, and it blows and sublimes away the snow, and what's left beneath is the blue ice of the glacier. And as that continues to sublime away, you go deeper and deeper into the glacier, and any rock that happens to be in the ice gets exposed, because the rocks do not evaporate, but the ice does. And so ultimately, you may have several thousands of years of meteorite collection with the meteorites just lying there on the surface, and the surface vaporizing away and exposing meteorites that are deeper below. So that means the blue ice fields are ideal for hunting for meteorites. And we had planned to take boats to search. This was the later expedition, search into Shermaka Oasis. In the Antarctica 2000 expedition, we were going to the South Pole as well as to the Teal Mountains and the Patriot Hills. We flew from Huntsville to Punta Arenas in Chile, which is down in Tierra del Fuego, very, very southern Chile. And we had a few days there of preparation, of briefings, of plans. We had a person who was a polar explorer with us that knew a great deal, and in fact was a pilot. So we were very well prepared, and we loaded all our equipment in a C-130 Hercules. And when we took off from Punta Arenas, I was sitting in the far rear, right in front of our gear, far rear passenger seat, and sitting next to me was Jim Lovell, and next to him was Owen Garriott. And we had, of course, in that time, we had GPSs, and nobody had a cell phone. Everybody had a GPS. We had iridium telephones. There were satellite phones, and every one of us had an iridium phone. And it took it was almost 8 hours to get to the, 7.5 to get to the blue ice fields. And when we flew across the continental shelf of Antarctica, not much beyond that, my GPS went nuts. It said, okay, I can tell the latitude. I don't know what's going on with the longitude, but I can give you altitude and latitude, and this longitude is absolute nonsense because the lines are all converging together. And we came in. We could see the Patriot Hills, the Black Mountains. We could see the blue ice, and as we came down to land, all of a sudden, we flew into a bottle of milk. It was astonishing. It was clear blue sky, and then you couldn't see anywhere. A snowstorm had just cropped up out of nowhere, and I couldn't see the mountains, I couldn't see the ice, and we're all leaning over, looking out the same window, and all of a sudden the throttle goes to the firewall, and I said, we're doing a go-around. And Jim Lovell says, no, we're not. I said, yeah, I think he's doing a go-around. He said, Richard, we're going home. I said, what? And just about this time, the pilot announced that he had aborted the landing, and we were headed back to Chile.
Oh.
Here we were. We had touched Antarctica almost. And then this silly pilot is saying, no, we're not going to land. We're going home. And I thought about that for a second. I looked at Jim. I said, this is all your fault. My fault, he says. Why do you say that? I said, you've got a habit of doing this. You go to interesting places. You get to where you go. You fly around a little bit, and then you go home without ever bothering to land. He says, I kind of do that, don't I? Because he had flown to the moon on Apollo 8, and then he flew to the moon on Apollo 13. And just a few months before that, he had flown a private plane to the North Pole. And as he approached the North Pole, the plane that had been flown there before them had landed on the ice at the North Pole, the geographic North Pole, and its landing gear had sunk into the ice. And so Jim gets ready to land at the North Pole, and he had to abort his landing and go back. So that was the third time. When I told Miriam this story, she said, surely you didn't do that. And when we met with Jim in Chicago, the first thing he did was told Miriam the same story.
Oh,
she said, oh my God, he really did. So we head home, back to Chile, into a headwind. And we're on a C-130. And when we finally got back to Punta Arenas and landed, we got off the plane, and Jim and Owen and I walked toward the front, and the pilot stepped out, and he looked very strange. And Jim says to him, how close was it? And he says, way the hell too close. He said, how close is that? He said, we've got 15 minutes of fuel left.
Oh my God.
Here we had come across the Antarctic Ocean and the Straits of Magellan, and we had 15 minutes of fuel to spare. If he had done one single go-around, we would have been in the water. So the pilot knew what he was doing by aborting the landing when he did. And so we survived. And then, that was interesting. It was wonderful in a way, because we got back. They had sold our hotel rooms to somebody else, because now we're arriving early in the morning. And they knew we were coming back, so they had made arrangements for a place for us to stay. And we got to the new hotel, and totally dead tired, because you can't sleep on a C-130. And so incredibly noisy, you can barely talk. And, well, you actually scream is what you do. And so we go in, we decided that what we were going to do was sleep until about noon, and then go find some breakfast and lunch kind of thing. So we got up around 12 o'clock, and we headed into downtown Punta Arenas, and we're walking along trying to find something to eat, and there's a pinball arcade sitting there. And lo and behold, about 10 feet away from the open door, there's a pinball game. And we looked in and we said, my God. So we walked into the pinball arcade, and I went over and bought a couple of dollars worth of tokens. And we came back and we started feeding in the tokens into the game, because we were playing gym level Apollo 13 pinball arcade.
What?
Yes, a pinball game with Jim Lovell's picture on the front of it, and we're all running around taking pictures like idiots, like, oh my God, isn't this cool? You know, and the boy that sold me the tokens thought, what in the world is going on? So he went and apparently told his parents that there were some nut people out in front. We were the only ones there. And his dad and mother came out. And then when they discovered that was Jim Lovell playing their Apollo 13 pinball game, they went to the cash register and brought us a big handful of tokens for free.
Wow.
And so we stood there for a couple of hours forgetting we needed to go eat. And nobody could beat Jim Lovell. I accused him of cheating, and he denied it. And then we found out that when Bally had made this Apollo 13 game, the first one they made, they gave to Jim Lovell and put in his game room, and he had been playing the darn game for a couple of decades before we challenged him in Chile. So we stayed there. We had to stay for 72 hours because of the pilot restriction.
So did you ever make it back to Antarctica after that?
Yes, that was the first expedition, and we had a fabulous stay there. We stayed at the first at the Patriot Hills, and then we went to the Teal Mountains, where we collected meteorites.
So you did find meteorites?
Oh yes, we found 20 meterites in the Teal Mountains. 20 meteorites.
Meteorites?
Yeah. In the Teal Mountains,
in the
yes.
Teal Mountains of
Antarctica. And, in fact, I've got a picture I can let you have of the one of the big, beautiful meteorites that we found on the blue ice.
Yes.
And
make it sound so easy.
Well, it is. Yeah. Well, actually, what you do to find meteorites in the blue ice is we took 3 snowmobiles with us, and we would get on the snowmobile, and then you would go driving around, and when you saw a rock, you drive over to it, and if it has sharp edges and so forth, you can tell, no, not a very good candidate. But if it has rounded curves where it had been ablated and vaporized as it came through the atmosphere, you would stop the snowmobile, get over, sometimes get down on your hands and knees to look at it. And if you were satisfied with the way it would look, then you would take the exact GPS coordinates, and you would then record the details and collect the sample in a sterile manner, because we were concerned about contamination. And so we actually brought back 22 meteorites, and 2 of them were not meteorites. So we had 2 rocks that looked kind of like meteorites, and 20 meteorites that looked kind of like rocks. But our approach all along had been, it is better to bring an Antarctic rock back and find out later it's not a meteorite than to leave a meteorite and by thinking it was a rock. Of course, they are rocks, but they're very special rocks.
Right.
So after we stayed a few days in the Teal Mountains, and in fact we were in our tents in the Teal Mountains, and one of the things we did is we took our saws and we cut big blocks about the size of bales of hay out of the snow, and we built a semi-igloo, digging a hole into the snow about 100 meters away from our camp. And so this was like an igloo with the half of it pointed toward the South Pole. And when the wind would come, it would hit this embankment and fly up over, and we had a nice pit about 4 feet deep. And down in the bottom of the pit, we put one of the fuel drums with a toilet seat lid on it, and its regular lid off. And it was also with a steel sack kind of garbage bag that could be pulled up around it. And so that became what we called affectionately, since Jim Lovell was the chief architect, we dubbed it the Lovell-Loo. And it was really nice because even though we had ladies along on the expedition, Amanda Onion was there, and there was a school teacher that was teaching her students about Antarctica. And what we did is we had a big pole. We put a black flag on the pole, and when you went to visit the facility, you turned it to where the flag was up in the air, and when you left the facility, you closed the door by turning the pole upside down and sticking it into the snow where the flag was right on the top of the snow. So from any distance away, you knew if it was okay to visit the facilities. And in fact, it was wonderful visiting the facilities because when you got down there, it was warm comparatively, because all of a sudden you were out of the snow. You were absolutely safe. You were completely out of the snow. And that was amazing.
That was a great experience.
I'm not out of the snow, out of the wind. Out of the wind. And in fact, a couple of days after that, we knew that there was a storm coming in, and so we proceeded to batten down the hatches because polar storms are not to be sneezed at, and so we got everything. We dug blocks again to put around the edges of the tents. And when we went into the tent that night to go to sleep, amazingly, it got dark, because one of the first things about Antarctica when you're there in the summertime is the sun never sets. It just circles above you like a big lazy orb circling overhead, and you can tell what time of day it is by where it's located, but you can't tell day from night. So, of course, we used our watches to do that. And we got in the tents, and it was a terrible storm. And the next morning, I was awakened early, thinking that I really wanted to visit the facility. And the thing that was surprising is I could see that it was sunny again, because the tent we were in was no longer black like it had been when the storm came through. And this terrible wind, we were wondering if we were going to get blown away. But when I decided to go to the facilities, I went across Paul's feet and unzipped the inner zipper of the tent, and there's a little room there. I had already slipped on my parka and my windsuit because I was going outside, and I unzipped the outer door to see nothing but snow all the way up to the top of the door. And I thought, oh my
It
God.
had accumulated.
It had accumulated. It had covered the complete doorway. We got one door. How am I going to get out? And I thought, should I use? No, I don't want to use my knife to cut a slit in the tent. No, not a good idea. We need this tent. So I started clawing like a dog, and I'm pulling snow inside the anteway and digging, and finally I see a little sliver of blue sky, and I'm all of a sudden realizing that I'm starting to sweat. And so I unzipped my parka and I took off my outer gloves and I dug, and finally I got the hole open to about like so. And when I had it big enough for the upper part of my torso to come through and squeeze up the top of the tent, I came slithering out onto the snow like a snake and got out on the snow, and I stood up, and there was absolute perfection. The snow, as far as the eye could see, was pristine, not a mark anywhere, and you could see the curvature of the planet Earth and these little yellow tent tops sticking out here and here and here, where people were inside peacefully sleeping as I'm planning to go to the level loo. And I looked out and I thought to myself, my God, this is the most beautiful thing I have ever, and I didn't get to finish my sentence to myself, seen in my life, because wham, a gust of wind hit me in the chest, and it was about 40-mile-an-hour wind at around 45 below zero. And my coat is completely unzipped. And one of the things we had been told before we left for Antarctica was to remember the 30-30-30 rule. And the 30-30-30 rule was that in a temperature of 30 below zero, in a 30-mile-an-hour wind, exposed skin freezes in about 30 seconds. And here I am with my parka unzipped and everything. Well, actually, I had my parka was unzipped, so I couldn't zip it up with the gloves I had on, so I took off my gloves again and zipped up my parka. And then I looked down and I thought, why are my hands hurting? And that's when I remembered the 30-30-30 rule. And I decided, okay, my hands are hurting because they're freezing. and at that time, I decided I didn't have time to try to put on my gloves, so I stuck my hands down in the pocket of my parka with my gloves wrapped tightly in my left hand, and like a penguin went running for the cook tent, which was a much bigger tent. And fortunately, the door of that one had been facing in the opposite direction. So when I got there, it was perfectly easy to pull out my hand and unzip the tent and go inside and zip it back up again. And I went in and I sat down on one of our stools and I started blowing in my hands because they were hurting like mad. And I've been sitting there blowing on my hands for about 5 minutes. I had forgotten what the purpose of the expedition was by this point in time. and I hear the zipper opening up. Now it's about 3:30 or 3:45 in the morning, and I'm thinking, oh, somebody else is coming in. And the zipper opens, and in walks Commander Lovell. Richard, what are you doing in here? So I told him my tale of woe, and Jim looks at me and he says, dummy, don't you know you should zip up your parka before you go outside? I said, that's a really helpful hint, Jim. I'm going to try to remember that in the future. And so we sat there and chatted after I got my hands unthawed to where they were not hurting so bad. But he put on some coffee, and we had a wonderful morning in spite of the partial disaster that almost happened.
Goodness. So for any aspiring young astrobiologist out there, would you recommend that they take a trip down to Antarctica to try to look for some meteorites themselves?
Well, actually, I think any astrobiologist, in fact, any not just an astrobiologist, but any young person who is interested in adventure and beauty, danger. There is danger there. There's no question about that. But it is truly one of the most remarkable places on the planet Earth. The beauty is absolutely exquisite. But I discovered that there are two types of people, and so they need to think about what kind of person they are before they make a decision. One type of person absolutely loves Antarctica, and another type of person hates it the instant they set foot on the snow. And there you get people that arrive there and want to go home immediately because it doesn't have the conveniences of home. I went for almost 6 weeks without taking a shower, but it doesn't matter because nothing smells in Antarctica. So your nose absolutely says, I'm not going to work. I'm not going to do a thing for you. Forget it. Nothing. Oh, it was wonderful. We had Thanksgiving dinner there, and our Thanksgiving dinner was amazing because before we left, no, this was the next expedition that we had Thanksgiving in the Shermaka Oasis in the Patriot Hills was the first, and the Teal Mountains was the first expedition. Let me stay with that for a second, because after we left the Teal Mountains, we flew on in our plane to the South Pole, to the Amundsen Scott Base, and we arrived unannounced. Now, you pop into somebody's house. Can we spend a few days here? Well, since we were unannounced, we would have probably had to sleep on the snow and the ice, but we had a couple of aces in the hole. We had with us two very famous guys, Jim Lovell and Owen Garriott. So even though the Amundsen Scott base was completely full, no bed anywhere, we got invited to bring our sleeping bags in and sleep on the floor of the gymnasium. So, and they even had some thin foam rubber pads to put down for us. So we slept for about 3 nights on the floor of the gymnasium at the South Pole. And I regret one thing, they had some things to sell. I actually got my passport stamped, the South Pole, and it was signed by Jim Lovell as the person who was in charge of customs and immigration.
Where you went to school, I have here that you attended Henderson State University, Duke, UCLA, University of Arkansas, and University of Alabama. Mm-hmm. Okay, as a student?
Yes.
Okay. You majored...
An instructor, yeah.
You majored in mathematics, physics, and French.
With a minor in chemistry.
Minored in chemistry. Yeah. Mm-hmm. Which of those universities were you teaching at?
At the University of Arkansas. Was an instructor up there while right before I left and came to Marshall.
Okay, so you also were a professor at the University of Buckingham in the United Kingdom.
Yes, that's an honorary professorship. In fact, that's one that was set up for the Astrobiology Center by Chandra Wickramasinghe.
Tell us about the Doctor of Sciences at the Russian Academy of Sciences.
Yes, on the 21st of October 2021, I was awarded Doctor of Sciences honoris causa at the Russian Academy of Sciences, and the award was given by the President, Alexander Sergeyev, in the Presidium of the Russian Academy of Sciences. This was based on a nomination that was made by academician Alexei Rozanov some 2.5 years earlier, and they had to have all of my academic credentials, scientific papers. I gave them a list of some 400 publications in peer-reviewed journals and conference proceedings, and I think at that time it was 45 volumes edited as well as authored. And then that went to the members of the Russian Academy of Sciences, and in order for this to be awarded, it had to be approved by the membership. So that happened on the 21st of October in 2021. The Russian Academy of Sciences is, of course, very prestigious, and it was indeed an honor to receive that award. After that, I was the following spring awarded Professor Doctor of Science for Ilia State University in Tbilisi, Georgia. Forgot which location it is, in Tbilisi. And that was also based on my work on microfossils in meteorites and studies of extreme microorganisms in glaciers and geysers and the various locations that I've explored microbial life around the world.
You had a long career at NASA, starting in 1966, is that correct?
That's correct. I was, after I left Henderson State, actually it was originally, at the time I was there, it was called Henderson State Teachers College before it became Henderson State University. After I left Henderson, I went to Duke University. I went there I was planning to be a cosmologist, so I was very much interested in theoretical mathematics, and I went there to study with Professor Hare to do work in infinite dimensional vector spaces. One of the fascinating things is when I was at Henderson, well, even before, I fell in love with the French language, and I took every course that was available in French at Henderson, including all the great masters of French theater, French drama, French literature. My favorites were Théophile Gautier and Charles Baudelaire, and then, of course, the great masters of drama. So when I went to Duke to on a National Science Foundation grant, as I was awarded this fellowship, I arrived at Duke University to find that Professor Hare wanted to go through the Nikolai Bourbaki volume on infinite dimensional vector spaces, topological work. And the problem he had was he didn't understand French. So my task was to translate the book and struggle through the mathematics while he got his own translation of this small Bourbaki volume. So I did that, and then I came back and went to the University of Arkansas, and I was teaching physics and general science at the University of Arkansas, and had been there for about a year when a friend of mine came to me and said, let's go to the library. And I said, but buddy, I said, it's Sunday. The library's closed. Oh, no. He says, it's open. So I went over with him. And the reason we went was Buddy Dawson had the intention of getting a job. So I just tagged along to chat with him. And while I'm there, I'm browsing around, and there was this table, and I talked to people there. They were from NASA, and they asked for some of my information about me. And then about 2 weeks later, I got a call from von Braun's office, and they wanted to know if I would be interested in coming to work at the NASA Marshall Space Flight Center.
Wernher von Braun.
Yes, and so I then talked with the people there, and they ultimately made me an offer by telegram. In fact, it was quite shocking because when I was staying in a boarding house, and the little lady that ran the boarding house came to me and says, "Richard, you've got a telegram." And I thought, oh my gosh, who died? And it was a telegram offering me a job I was making like $1,200 a year at University of Arkansas, and they offered me $7,500 a year to come to the NASA Marshall Space Flight Center. I went to the professor that I was working as an instructor, and told him what had happened and asked him if it would be okay for me to leave at the end of the semester. And he said, well, you've got to. I said, I've got to. He said, if you're so stupid that you would not accept a job like that, you're too stupid to teach anything in physics or physical science here. So I realized that was permission. And so I accepted the post and left and went back to my home in Arkadelphia for a few weeks. And then when I came to Marshall, I thought I was going to be working in fluid and flight mechanics. But when I got here, I just discovered that they had decided they wanted me to work in optics. Because actually I was doing X-ray diffraction research at the University of Arkansas, and they were very much interested in all the matters related to X-ray diffraction and X-ray optical systems. So the first work I did at NASA Marshall Space Flight Center involved several things. One on the development of a multiple pinhole telescope in collaboration with George Stroke to do a random array of pinholes for astronomy, to do a posteriori or holographic deconvolution of the array of images, so that you could take an image with a bunch of apertures and you would get an image that would be vastly brighter than with a single pinhole, but then you could squish them all back together by a synthetic technology that George Stroke had developed and make a much brighter image. So that was the plan. And while I was doing that, I wrote a computer program to actually do this fabrication of a random array of apertures of different configurations. And after I had some of these made and reduced in size by a photographic technique that I developed, I was looking through my plates one day and looked out the window, and lo and behold, I saw the sunlight shining on chrome automobile bumpers. That day and time, cars had real bumpers with chrome. And every place that the sun was shining was a beautiful color Fraunhofer diffraction pattern. Well, that was astonishing because everybody knew that you needed coherent light to get a Fraunhofer diffraction pattern. And here I was seeing it with white light. And in addition to that, I was seeing the diffraction patterns that I had taught at the university, but there I would have to set up an aperture and a bright light and set up a traveling microscope, and then in the focal plane of the instrument, the student could look in and see the diffraction pattern of a single slit or a double slit or a circular aperture. And then they would bump the microscope and I would have to go realign it and get it prepared for the next student and so forth. And it was a long and tedious process to teach this. And here I was seeing single slit and double slit patterns by just holding up a plate and looking through it. And I was also seeing patterns in brilliant color. This was impossible. So I immediately realized there had to be a reason for it, and I went to my big, thick Principles of Optics by Born and Wolf. And when I went through the equations on Fraunhofer diffraction, I realized, yes, it was not only possible, that was what was happening. So I then submitted an abstract to give a paper in 1968 at the Optical Society of America on classroom demonstrations of Fraunhofer diffraction, saying that, hey, we could make these things and you could teach your students about the diffraction patterns of different kinds of apertures, where that they didn't have to have a microscope. They didn't have to have a single aperture and a bright light. They could just have an array of these apertures and look through a photographic plate or piece of photographic film, and they could see what the aperture was producing. I gave that talk in 1968 at the Shoreham Hotel, and afterwards, well, in fact, it was wonderful because I'd made up about 100 of these diffraction plates photographically with a description of exactly what you were seeing. And at the end of my talk, my friend Charlie Hawkins had made a box for me that had a automobile taillight bulb on it and a toggle switch and a 6-volt lantern battery inside. And when I finished my presentation, which was astonishing to me because the room was completely filled with standing room only, and I ran out of my plates, so people had to share them. And when I finished my presentation, they turned off the light, and I flicked on the car tail light, and there were oohs and ahs all over the room as they were seeing single slit and double slit. They were seeing telescopes with Cassegrains with small apertures and large diameter primaries, and with 3 spiders and 6 spiders. And here they were seeing the diffraction patterns that you would see with a telescope, with a big telescope like the Mount Wilson Palomar Observatory, like telescopes that we were developing for spaceflight. And then I had an array of apertures, and when they were looking in white light, they saw these beautiful colors. Well, only a month or so before that, a guy by the name of Franklin Harris had published a paper with the cover of Applied Optics where he reported he had taken the first photographs of white light diffraction patterns. And actually, they weren't the first because I had taken others using my technique, but I hadn't submitted to Applied Optics. And he had actually taken these by the same technique that I used in the schools, but he had set up a brilliant white light source and his aperture at at NIST and in a cable trace, so he would put his film camera about 100 meters away from the light source and then turn on the light and go to the camera and open the shutter and walk out and lock the door and come back 2 weeks later, or in one case 28 days later, to get his exposure. A single photograph after 28 days, and you saw color diffraction patterns. But the reds were all washed out into pinks and so forth. So they weren't beautiful, intense pictures like I was getting. And Frank Harris came to me afterwards and told me that he wanted to know if I would be interested in looking at verification of a book by F.M. Schwerd that he had bought years ago, published in 1835, called Die Beugungserscheinungen. And in that book, Schwerd actually calculated the diffraction patterns of arrays of apertures and drew what they looked like and then colored them. So here this 1835 book had colored images of white light diffraction patterns, and I made the same arrays of images that Schwerd had done theoretically and took photographs and was able to exactly replicate his calculations. And I submitted that to Applied Optics with Frank Harris, and we got the cover of Applied Optics with the photographs. And in fact, my Fraunhofer diffraction patterns were published in the McGraw-Hill Encyclopedia of Science and Technology and Encyclopedia Britannica, in many classic optics texts. And in fact, the other person that came to me after my talk, he congratulated me and said, I would like to include this in my book, but the publisher tells me the damn thing's too big already. And I'm thinking, what book is he talking about? And then he stuck out his hand and he says, allow me to introduce myself. My name is Emil Wolf. I caught myself because I almost said, "My God, I thought you were dead," because he had written Principles of Optics with Max Born, and nobody that does things with greats like that could possibly still be around and talking to you. And it was kind of funny because years later, when I was president of SPIE, we were with M.J. Swallow at his critter roast in Florida, and I'm sitting at a picnic table eating alligator, and Emil Wolf came over and sat down next to me, and I told him this story of what had happened so many years ago. And when I told him what I had almost said, he laughed and he said, "Well, and I'm still not dead."
So you've had a long career in optics before you even worked on astrobiology.
Yes.
Right?
In fact, let me go back to my major job at NASA. This was sort of a side event.
Okay, yeah.
When I
And this was all at the Marshall Space Flight Center.
my entire career at NASA was at the Marshall Space Flight Center.
Okay.
And when I first arrived, the major project that we had, this is something I came up with entirely on my own. Just fell out of this work with George Strout and Jim Underwood. But when I first arrived at Marshall, I was told two things. Went to see my boss, James C. Taylor from Texas, Tex Taylor, and he told me that in order to work in optics, I needed to know what optics really was like. So the first job that he gave me was to build a paraboloidal mirror for an optical telescope, and I had to grind and polish it entirely by hand. And I was told that I had to achieve a 20th of a wave precision. So I went to the optical shop and, working with the people there, made a pitch lap and came back into the dark room and started laboriously grinding and polishing this mirror by hand. They had an optical shop that could do it by machine, but I was told no, I couldn't use the machine. It had to be done by hand. And then I would polish, and then I would go and test, and then I would come back and polish and go and test. And finally I got tired. I would polish for about 15 seconds and test for an hour. And so I decided it's going too slowly. I polished for about 3 minutes and went and tested, and the interferograms looked funny. And I called my mentor, Daryl Evans, over. And he said, "Well, Richard," he said, "you know what's happened?" I said, "What?" He said, "You rolled the edge." "Oh, okay." I said, "Well, how do I fix that?" He said, "Well, go get some number 100 grit." That's where I started months earlier. I had to grind the mirror back to a sphere and then bring it up to a paraboloid. But this time it took much less time because I knew what I was doing. And when I got to the final stages, I was very, very much more careful. So after I did this grunt work of learning the characteristics of mirrors and the precisions of optical metrology, because I was always told if you can measure it, you can make it. But if you can't measure it, you can't make it. So the next step was in the development of the lunar laser retroreflector array, because we had started working on a plan to develop a technology to fly retroreflectors, or optical corner cube reflectors, on the Saturn V vehicle. And actually, retroreflectors were made down in the optical shop, and they were mounted on the Apollo 8 Saturn V. And the purpose of this is a retroreflector is like the corner of a cube, of a box, made out of a high-quality glass. And when light goes in the square surface of the pyramid and it hits one of the triangles, it reflects to the opposite triangle and then reflects directly back out of the base, exactly opposite to the direction it came from. So if you point a laser beam at a retroreflector, the beam comes right back to you. And So we built these, and then to prove it would work, we actually mounted some of these optical corner cubes on U-2 and SR-71 spy airplanes, and they flew them over Huntsville. We had built a very special telescope to use with this experiment. And as they flew them over Huntsville, we sent laser beams to the spy planes, and they hit the retroreflectors, and we were able to not only track it, but also measure the exact distance. And we got some of them traveling over at over 90,000 feet. But at that time, I couldn't talk about that because the fact that they were flying at 93,500 feet was not publicly accessible.
Gosh.
So then those mirrors were taken off of Apollo 8 because of weight constraints, and ultimately an array of them was carried to the moon and pointed back at the Earth by Buzz Aldrin, and they were used to measure the distance from the Earth to the moon to an accuracy of about an inch. And then an array was built and put in Apache Point, New Mexico, the Apache Point Optical Lunar Laser Observatory, as it was called, Apollo. NASA loves acronyms. And at that telescope, which was much bigger and much higher intensity and more precise pulsing of the laser, they were able and are still able to measure the distance from the Earth to the moon to an accuracy of better than a millimeter. And that made it possible to do all sorts of things, like precisely determine the universal constant of gravitation and so forth.
What got you started with extremophiles and finding microbes and permafrost?
I guess I need to tell you another story, and that is when I was a child, I became very interested in microbial life, and I got a microscope. I was in the 3rd grade when I got my first microscope, and I loved seeing microscopic organisms, amoeba and paramecia and rotifers and diatoms and all sorts of things. And to me, even though we had gotten a television set, I mean, this was a zoo. You could sit there and watch for hours as tiny little rotifers would run around eating poor little diatoms and other kinds of algae and gobbling up bacteria and all sorts of other things.
Watching microbes eat each other?
Watching microbes, and sometimes you could see the organism that they had eaten through the body and on the inside, and the structures moving and all of the wonderful things that were going on in these unicellular life forms.
What year was this?
This was in it was in the 3rd grade, so it would have been 1951. I started, is that right? No, I started in 1940. Yeah, I started in 1948, 1951 would have been the year. In fact, it was the year we got our first television set, and the year that shortly after that, I think it was early 1952, that I saw on television the explosion of the first hydrogen bomb at Inuit Atoll, which they broadcast live by some nefarious techniques. A TV group knew that they were going to set off an atomic explosion. The first atomic explosion was broadcast live, was from the launch site near the Trinity site, and that first explosion that they broadcast live, they had actually set up a telescope and a TV camera on top of a hotel in Las Vegas, and had it pointed in the right direction, so they were able to broadcast an atomic explosion live. But after I had gotten this microscope and become very interested in microbial life, I had then gone off to do other things, gotten very interested in astronomy with a telescope and so forth. And it was not until I was here in Huntsville working on X-ray astronomy And one of my friends, Charlie Murcia, professor at Alabama A&M, invited me to give a lecture at the Unitarian Universalist Church in Huntsville on X-ray astronomy. Well, I thought, this is strange, talking to a church on X-ray astronomy, and he insisted that the Unitarian Universalist members would be interested in this. So I agreed, and I took a view graph projector and a bunch of my stack of view graphs and went there one Sunday in 1968, right after I returned from my first trip to Europe, and gave my talk, and was a small group, 15 people or so, and I went over after it was over while they were preparing lunch for us, and I'm standing there looking at a bookshelf, and all of a sudden I hear this voice say, "What a pathetic library they have." And my eyes focused, and I all of a sudden realized that the library consisted of 4 volumes, Reader's Digest condensed books. And I looked aside to see where the sound had come from, and there was this beautiful lady standing there with blonde hair and blue eyes and a black skirt and white blouse and big white hat with a black brim. And I was totally astonished, and we chatted for a few minutes and then went and sat and had lunch that they brought to us. And while we were eating lunch, I thought, well, yes. So I asked her if she would be willing to go to dinner with me the following Saturday night. And to my great shock, she accepted, which I was quite sure she would call back and cancel at any point in time, but she didn't. And we went to a restaurant, and while we were eating, I told her about my trip to Europe and the photographs I had taken, and she says, "You like photography?" I said, "Yes." She says, "How would you like to photograph some of my diatoms?" Well, I thought, that sounds like an interesting idea. So it turns out that her name was Miriam, and her great-grandfather was Cornelius Onderdonk, who had studied diatoms in the 1800s. He was also the chief architect of the very interesting buildings in Rugby, Tennessee, where this colony had set up in the mid-1800s. And she had inherited his whole collection of diatoms. And so she brought me his diatom collection, and I borrowed a microscope from a friend of mine and started taking photographs of diatoms. And it was pathetic because I was using my Yashica camera, and I would wrap black cloth around the interface, and I would take a picture and then have to redo the alignment. And 10 minutes later, take another picture. And I kept doing this. My friend Finn Jakobsen came by and told me I couldn't take photographs of diatoms that way. And I said, well, why not? He said, you need camera adapter. And he explained to me everything I needed to do proper photomicroscopy, shutter cable release, etc. I said, well, Finn, I don't have those things, so I'm working with what I have. Well, after a few weeks, I had about 20 decent photographs, and I had spent about 15 rolls of film. And I took one in and showed them to Dr. Holliday, who was the one that let me borrow his microscope. And he said, this is interesting. You know, Chemical Engineering Week just had an advertisement from a company, and they show diatoms in their ad. And he showed it to me. And amazingly, it said, if you send us a request, we'll send you a set of free framing reprints of diatom photographs. Well, I was amazed that that might be possible. And since I wasn't going to be buying tons of diatomite for filtering beer and wine or swimming pools, in my letter explaining why they might be willing to send me their pictures, I mentioned that I had been taking photographs of diatoms myself. And lo and behold, a couple of weeks later, a box arrived with these beautiful 11 by 14 pictures, and I rushed out and bought frames for them and hung them all over my house. And a couple of weeks later, the phone rang, and it was the advertising manager for Grefco out in California that made the Dicalite diatomite filters. And he mentioned that he had read my letter, and he wanted to know if I would send him some of my pictures. Well, I said, yes, of course I will. And so I went and picked out my 20th best pictures. I thought it's the only thing I can do to repay them for what they sent me. And I took them to Kmart and spent $3 or $4 and got a set of duplicates and sent them off to California. And about 2 or 3 weeks later, the phone rang, and it was Kent Cochran, and he wanted to know if I would consider selling him my photographs. And I said, well, I hadn't thought about it. And he said, we want international rights, exclusive rights, so you can't publish them or sell them to anyone else. And but every time we publish one of your pictures, you'll get credit. I said, well, that sounds interesting. He says, how much would you charge us for the whole set? And I'm sitting there thinking, my goodness, I didn't know you could sell photographs. And all of a sudden, I had these bright visions that maybe they might be willing to pay me $100, $200. And so I said, possibly. He said, how much would you charge? I said, well, I haven't any idea. What would you entertain an offer? I said, well, of course. He said, well, for international rights, exclusive for the set, we're prepared to pay $5,000. That's what I said. That sounds fair. So
I'll accept.
He then sent me the release and all of this, and and the letter saying, we noticed these are duplicates. Would you be willing to let us borrow the originals to do the 3 color separations? I thought, oh my God, let them borrow the originals. So when I signed his release, I sent back the box of originals and said, this is not loan, this is what you're purchasing. This is not for loan.
No problem.
And so a few days later when the check arrived, I called Miriam and asked her if she would like to go to the Carriage Inn for that Saturday night. Well, she was shocked because that was the most expensive restaurant in Huntsville. And I know she was wondering what in the world was going on. And when we went to the Carriage Inn and we're having dinner, I said, the diatoms you loaned me, I sold some of my photographs. Oh, she said, that's great. And I said, yes, and they're your diatoms and my pictures, so I thought I would like to share my check with you. Oh, you don't have to do that. I said, I know, but I said, I want to. And I handed her the check, and she almost fell over when she saw it because she was teaching school at an elementary school here in Huntsville, and I don't think she was making much more than $4,000 or $5,000 a year. At that time, in fact, I'm sure it wasn't, because my salary at the time at NASA was $7,000 a year. And so we went down the following Monday and cashed the check, and she opened her account and I opened my account. And that was my Miriam that I married 2 years later in August of 1970. And we were together until I lost her in 2012. So she used to tell everyone, I only married her to get her diatoms.
I remember you telling me this story about how a pretty girl got you into diatoms.
That was it, yeah.
I didn't know it was Miriam.
Yeah. And she was a scientist. She worked at Marshall Space Flight Center after she left teaching school. In fact, she worked in Bob Springhammer's lab. And one of the projects she was working on was odor control for spacecraft.
Odor control.
Odor control. Turns out, sometimes astronauts make gases. And
It all comes back to gas, doesn't
it
it?
all comes back to gas. And so their work was, how do you control these problems? And so they would take hydrogen sulfide and all sorts of noxious kinds of tremendously odorous gases. Of course, hydrogen sulfide smells like rotten eggs. And they had all of these different chemicals. Well, she had her master's degree in physical chemistry was her background. And so she was hired by NASA to do this kind of work. And then they would use a gas chromatograph, and they would look at the chemical composition of the odor, and then they would pass it through the various filter kind of systems they were using, and then see how it had changed. And one of the amusing things is she was asked to give a presentation to Dr. von Braun. And she had all of these different gases, odorous gases, in balloons of different colors, and her gas chromatograph to explain to Dr. von Braun exactly what they were doing. And he showed up with a complete entourage, of course, as he always did. And Eberhard Rees, his deputy, was there, and Ernst Stuhlinger, the director of the Science and Engineering Director, Associate Director for Science at NASA Marshall, and the lab directors, and her lab director, and her division chief and branch chief. And there were all these balloons filled with helium that was the carrier for the gas, attached to a bar, and they're floating in the air. And poor Miriam was petrified. Here she was giving a presentation to Wernher von Braun himself, and she was obviously frightened. And all of a sudden, one of the balloons starts going up and down, and it was Ernst Stuhlinger who had hold of the string, and he was dropping this balloon down and then letting it go back up. And everybody stopped. She stopped talking. Everybody looked at Dr. Stuhlinger. "I so love balloons," he said. Everybody almost fell over laughing. And Miriam then completely relaxed and was able to go on and give her presentation properly. And I've discussed this with many people, and we all agree that Stuhlinger did that on purpose because he knew she was nervous, and he knew that something like that would probably change the situation, and it did.
Well, that was nice.
He was one of the most wonderful people I ever knew.
So you had an early childhood fascination with the study of microbiology. You met Miriam many years later. Turns out she did too.
Yes.
So the two of you together just reinforced this inspired approach towards your research. And after this many years later, you studied astrobiology for NASA.
Well, actually, I studied astrobiology before there was astrobiology. In 1985, I received an astonishing phone call. Well, I should go back a little bit earlier than that. In 1969, I proposed to write an article on diatoms for National Geographic. And I sent them a bunch of my photographs, I think about 500 photographs.
500?
Yeah, several sets, all in these nice holders, and proposed an article on diatoms because I'd been taking a lot of photographs since I started in 1968. And they kept them for a while, and then I was told that, they had decided that they were going to have an article on algae done by their own scientist by the name of Paul Zahl, and they thought he would probably cover diatoms in his article on algae. Well, I was rather upset about this. I thought, here, I suggest the idea, and then they go and get somebody else to do it. And so, being upset, I called them up and said, okay, send the pictures back. I'll publish them somewhere else. Well, they did. I thought, uh-oh, darn it, maybe that was the wrong approach. And but I got busy at that point in time with other work with NASA, and I was doing all sorts of other things, and so I never bothered to, well, I wrote a couple of little articles on diatoms and published some of the pictures, but nothing big like National Geographic. And then in 1973, well, at that point in time, we were developing the X-ray telescope that we planned to fly on Skylab. And I was working with Jim Underwood, Dr. Underwood at NASA Goddard, who was originally going to be the principal investigator of Apollo Telescope Mount Experiment SO56. But since he was British citizen, NASA wouldn't allow him to be PI. So Jim Milligan became principal investigator, and Jim Underwood became a co-investigator. And then later, I became co-investigator as well as Tony DeLoach on Apollo Telescope Mount Experiment SO56, which was to design and build an X-ray telescope for solar research. So I had gone to Johnson Space Center, and we were doing our training and preparations and plans for the Skylab mission before Skylab flew. I would go down to Houston and spend a week and come back and spend a week at Marshall, and so I was going back and forth. And the phone rang, and it was Miriam, and she says, have you heard from National Geographic? I said, no. She said, they're trying to get in touch with you. And I said, really? So she gave me the number, and I called back, and they wanted to use two of my photographs in Paul Zal's article on diatoms, on algae. And they said they could send me copies of the pictures that they wanted the originals from. And at first I was outraged because I all of a sudden discovered that they had kept duplicates of every photograph I had sent them. And then I thought, well, maybe I shouldn't be mad. They're going to give me credit and they're going to pay for the photographs. So at that point in time, I went back home and I dug up the originals and sent them off to National Geographic, and they published them. But then about a year later, I got a call from National Geographic saying they had reviewed my pictures and decided that they wanted to do an entire article on diatoms. So I then sent a draft, and they took my draft. In fact, they told me that they would have to put it in their own style, and I said, what do you mean? Well, we're going to rewrite your manuscript in National Geographic style. And they said, but don't be upset. We do that to everyone. And I said, really? He said, yes. He said, we had an article written on Abraham Lincoln by Carl Sandburg. And at the banquet, Gil Grosvenor stood up and announced in front of Carl Sandburg that they intended to rewrite his manuscript. A guy that knew more about Abraham Lincoln and had written enormous numbers of words on the subject. So anyhow, I said, okay, that's fine by me, as long as I get to check it to make sure everything is scientifically accurate.
Right.
And in fact, I had to make a couple of critical corrections. One of the things they had changed is they had talked about how many trillions of diatoms were in the White Cliffs of Dover. And I called them back and said, well, I don't understand. Why did you say that? And they said, why? Is there something wrong with it? I said, well, yes. I said, White Cliffs of Dover are chalk. They're not diatoms. They're made out of coccoliths primarily. They have very few diatoms in them. Really? I said, yes. And oh my goodness. And I said, how did this come about? And he said, well, I'm sorry about that. He said, that was my fault. He said, about a week ago, I was at a cocktail party with this guy from England, and he mentioned about how many trillions of diatoms there had to be in the White Cliffs of Dover. So he put it in the article.
Cocktail party, huh?
Cocktail party science. So
sometimes it works for the better, sometimes not so much.
Anyhow, what happened was that article was published in June 1979. And National Geographic paid very handsomely for it. And ultimately, a few years later, I got this phone call based on my article in National Geographic. And there was this very strong British voice wanting to speak to Richard Hoover. And I said, yes, I'm Richard Hoover. Well, my name is Fred Hoyle. Well, I could have fallen out of my chair because Fred Hoyle had been my childhood idol. He was the one that explained the way in which elements are formed within superhot stars. Brilliant astronomer who coined the phrase the Big Bang, and whose cosmology was the steady state theory of the origin of the universe. The Burbage, Fowler, and Hoyle paper that was published in, I think, 1956 was the paper that resulted in Willie Fowler receiving the Nobel Prize in Physics. So Fred Hoyle was an absolute genius, one of the most brilliant people I ever met in my life. I think probably the most brilliant. And here was Fred Hoyle wanting to talk to me about diatoms. I was shocked. And then he told me that the reason he wanted was to find out if I could get some diatoms for him. And when he learned that I was actually doing research in X-ray astronomy and also in solar physics, and was working as an astrophysicist at the Marshall Space Flight Center at the time, he asked if I would be interested in working on a scientific paper with him and the student that was now Dr. Professor Chandra Wickramasinghe. It took me a couple of nanoseconds to think that one over as well. And so after I told him that I would be delighted to do that, not long after that, Chandra Wickramasinghe came to visit with me, and he stayed several days, and then he went back to Cardiff. And then
this is roughly what year?
Oh, let's see, this was 1985. 1985. And a month or so after that, Fred Hoyle and Lady Barbara came, and they stayed in my home as my guest. And in the mornings after breakfast, Miriam would go in to do the dishes, and Lady Barbara would come in and insist on helping with the dishes. Miriam was so astonished at having a real lady insist on helping her with the dishes. And Fred and I just hit it off wonderfully. He was amazing. And we talked about diatoms and all sorts of things, the steady state theory, which, by the way, at that point in time, he had concluded that he had made a mistake. And the mistake, he said, was the most serious and grievous error he made in his entire life. And that was in acquiescing to the Big Bang theory. He was at that time convinced that the Big Bang theory was wrong and that he should have stuck with his guns on the steady state theory. And I think he was right, because now we're finding out that the James Webb Telescope is finding giant galaxies in the cosmic dark ages that shouldn't be there. And now they're trying to figure out how to put some epicycles together to explain the giant galaxies in regions where they should not possibly be, only a few 100,000 years after the Big Bang. Well, maybe the Big Bang didn't happen 13.8 billion years ago. Maybe it was 26 billion years ago, or maybe longer. So now we're going into maybes in science.
I may have mentioned this to you before, but I want to pass along some words from Dr. Brandenburg, who is a big fan of your work. He truly believes that, well, I'll just go ahead and say it. He truly believes that NASA has unfairly marginalized you, has unfairly, marginalized your work. And, it sounds conspiratorial, but given the evidence put forward, it does seem like, well, to some people, it seems like they might be trying to silence you and your discoveries. But again, he is a big fan of your work. He believes your work will ultimately contribute to this overall topic of disclosure we're talking about. And Mars has a big part to play in that, and I agree with him. You guys disagree on Orgeal.
Brandenburg and I,
On its origin.
on its origin. Well, okay. I don't have any problem with that because, quite frankly, I have no doubt whatsoever that the evidence is very, very solid that the Orgeal meteorite came from a comet and is not a meteorite from Mars. There is a group of meteorites from Mars, namely the Shergottites, the Knocklites, and the Chasignites. And they are known to be from Mars because studies have shown that the gases trapped within these meteorites, the noble gases trapped within the meteorites, match the noble gases in the atmosphere of Mars. So that gives solid evidence that those meteorites, like Allan Hills, are from Mars. The problem with Orgeal is it's not at all like the SNCS. In fact, it is like only the other CI1s. For one thing, you drop a rock from Mars in a glass of water and it falls to the bottom. You drop a piece of Orgeal into a glass of water and it disintegrates completely. You have nothing but a black mud at the bottom of your glass of water. And that's because it is basically interstellar dust particles held together by magnesium salts, magnesium and ammonium salts, primarily magnesium sulfate, which is the dominant mineral, one of the dominant minerals of the Orgeal meteorite. Magnesium sulfate is not a dominant mineral in the Martian meteorites.
What would Allan Hills do if you dropped it in water?
Oh, it dropped to the bottom just like any old rock. No question about it. It's a Mars rock. Yeah, it wouldn't disintegrate. Damn no. No. So I mean, I'm sorry, but Brandenburg needs to answer the question: how does he explain the relative position? In fact, I can show what is the position in terms of the oxygen isotopes. The oxygen isotopes in the Ci1 carbonaceous chondrites are totally different than the oxygen isotopes in the SNCS meteorites. So he's welcome to his opinion. I disagree, and I disagree on the basis of what I know about the meteorite.
One of the greatest things I could possibly do is to get you two guys in the same room to talk this over. At the end of the day, though, his concern is less about its origin, okay? And he considers your work having to do with these microfossils to be quite a discovery and should be applauded. So it's not a fight he wants to necessarily have.
And I'm saying he's welcome to his opinion. I would like to know how he explains these differences.
Yeah.
You see,
well,
the Orgeal meteorite is like the Alais meteorite. In fact, we have 10 of these Ci1 carbonaceous meteorites on the planet Earth. There are 10 of them, and there were 5 that were found, and the other 5 were found in Antarctica. But the first 5 were observed falls.
I can't speak in detail or at length as to what his argument is. I only know the basics. He proposes that a lot of the meteorites that we have are mislabeled. Now, I don't know the details enough. Like I said, if you're curious, I can follow up with you.
Uh-huh.
I don't want to spend any more time with this. I just wanted to pass along the good words from Dr. Brandenburg.
Thank you.
He really appreciates your good work.
And I mean, I just tell you the reason that I disagree. In my mind, there is solid evidence that the Orgeal meteorite most probably came from a comet. They're based on the orbital parameters, based on the elemental abundances, a wide variety of things clearly indicate to me that it was from a comet rather than from Mars.
Well, I'll pass this along, see what he says.
Sure.
Let's get through a couple
But he
of
knows
things.
that. He's heard me talk before. He knows that's my opinion.
Well, I heard you guys met, which is really cool. Wish I would have been there that day.
Yeah, he came to some of my conferences in San Diego.
Good. So you pass out these trading cards here, which is really cool. On the back here, you've got a photo of you and Wernher von Braun.
Yes.
Okay. Do I recall correctly, weren't you telling me a story about you two and watching a rocket launch?
That was the photograph of me and von Braun is because we were Fred Ordway and Mitch Sharp and many interesting people. And part of his group was a fashion designer by the name of Diane von Furstenberg. And several of us, Jeffrey Brown, I think that's the proper name, from the Yerkes Primate Center was there, and we went to go to the last launch of the moon mission, the Apollo 17 launch. Mitch Sharp and Dave Christensen was part of our party, and we were staying at the Ramada Inn in Orlando because we couldn't get room anywhere near the Cape. That was the last launch of Apollo Saturn mission. And we're sitting there finishing our lunch, just ordered our dessert, and we hear a booming voice, "Well, this is an interesting group, you mind if I join you?" And we looked up, and it was Wernher von Braun and Ernst Stuhlinger and Eberhard Rees. And he sat down. In fact, he sat right next to me and across the table from Fred, and they started chatting. He ordered a piece of pie for dessert. And we're sitting there talking for a little over an hour, enjoying dessert and chatting, and his handlers are going absolute nuts because they didn't want him in Orlando. They wanted him at the Cape. The launch was due to happen a few hours later. Yeah. And all of a sudden we hear whop, 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 and a helicopter landed on the grass of the Ramada Inn in Orlando. And he and Stuhlinger and Rees went out and got on the helicopter and flew off to the Cape. And we piled in my car, and it took us until after 6 o'clock to arrive there because the traffic was so heavy. In fact, when we drove back the next morning, the launch didn't occur until 12:30 or 1 o'clock, and it took us until almost 6 to get back to the hotel, and we decided we would check out at noon instead of check out at 7 and drive back to Huntsville. And when I woke up, there was a blurb on the television about an accident that had happened. And while I was there, I went and photographed several of the dignitaries that were there. And, you know, famous people, Marlene Dietrich, Zsa Zsa Gabor, John Wayne, King Hussein of Jordan, Spiro Agnew was there, the vice president. Nixon was off doing other things. But anyhow, I woke up to turn on the television, and there was this thing that there had been an accident. It seemed that King Hussein had gone and gotten into his plane, and as he was taxiing out, he bashed the left wing of his aircraft into the right wing of Air Force Two. And they said that he had apologized. He reportedly said, "I'm terribly sorry. I'll buy you another one."
Didn't you witness a rocket launch, though, up close?
Well, I mean, yeah, I witnessed many of them up close.
Weren't you supposed to be, you told me a story one time, I forget how the setup was, but you were supposed to be here to watch it with all your colleagues, but you got special access.
You mean when I almost got killed by a rocket?
Okay,
that time,
sure.
When I almost died. Well, we went to all the Saturn launches. So we would sit by the side of the VAB and watch the Saturns, but I never came anything close to perishing on that launch or those launches. But we had a launch from White Sands, a night launch for studies of the Papace supernova remnant. And since it was not a solar launch, and I had already done my alignment of the telescope and everything I needed to do, I wasn't required to do anything during the flight because that was all pretty much automated. So I got permission with some other guys. I found out they were going to go outside to watch the launch, and I got permission to go watch the launch as well. And Art Walker said it was fine with him. And so I told them, "Hey, I want to join you guys. Let's go watch the launch." So we went out. We stood in amongst a bunch of cars, and there we were a few hundred yards away from the launch tower there at White Sands Missile Range, where we were right by the side of the blockhouse, but we were in amongst cars that people had driven up and parked there, and we could hear the countdown over the loudspeakers, and we got to 0, and there's this tremendous bat out of hell kind of thing, and this rocket goes off like a bottle rocket. It wasn't like a Saturn. These Saturns are lumbering giants that barely move at first, and you think, is it really going to move? And this thing goes up like that, and lit up the whole area. I mean, it was just spectacular. And then we felt the shock wave and the vibrations and everything of the launch, and it goes up, and then we saw the staging where the first stage and second stage separated, and we saw the firing of the second stage, and it continues on up. And here's the first stage sitting up there, and it's getting brighter and dark and bright and dark. And I'm looking at it, and I said, "It's not moving." And one of the guys says, "Yes, it is." I said, "Do we have time to make it to the blockhouse?" Not a chance. And we're standing there.
What's the blockhouse?
The blockhouse was, I don't know, 50 yards away, something like that. You know, it probably taken us 20, 30 seconds. I don't know how long it would take it to run there, but maybe a minute, I don't know. But anyhow, he announced as how there's no way we could get into the blockhouse. And then all of a sudden I saw a little bit of motion, because it not moving was bad. That meant it was vertically overhead, falling straight back down. This is not good when it's falling straight back down. And all of a sudden, we started seeing a little bit more motion, then a high-pitched whine, and boom, like that, it landed about 50 yards on the other side of the launch complex. So it was about 250, about 2 or 3 football fields away from where we were standing. So it missed us, but
That's scary.
Yeah, it was scary. I mean, I realized that it would have been big news if a rocket scientist got killed by his own rocket landing on him. You know?
Let us talk about dimethyl sulfide.
Dimethyl sulfide.
Okay, so as I understand it, as you have explained to me, dimethyl sulfide is an organic substance. I'm going to break this down real easy for people, okay? It's an organic substance that, as far as we know, the only way that we can produce dimethyl sulfide here on Earth is through active microbial activity. Do I have that right?
Actually, we don't produce it by active microbial activity.
We don't produce it.
Microorganisms
the only way
produce it. The only way it
we
is
understand
produced
it is produced.
It's produced as a result of a complex set of enzymatic reactions, pathways. So it's the result of a complex suite of pathways that involve the conversion of dimethyl sulfonylpropionate into dimethyl sulfide. It is typically referred to as the aroma of the sea. It's that smell that you get when you're out on a sailboat on the ocean. You know, that's strange ocean smell that people recognize and know. And that's because the dimethyl sulfonylpropionate is converted to dimethyl sulfide, and that's what we smell. The most abundance of it comes primarily from the polar regions, from diatoms, sea ice diatoms, but there are a lot of other organisms. There are things like dinoflagellates. There are things like sulfur bacteria, a variety of other microorganisms that play a role in production of dimethyl sulfonylpropionate and dimethyl sulfide. Now, the point is that was discovered on an exoplanet.
Hang on, time out. Let me get to this,
All
okay?
right.
So, dimethyl sulfide, like we just discussed, the only way we know is a natural process, active microbial...
Complex natural process.
Complex natural process must
yeah.
produce this, okay?
Yeah,
It is
yeah.
not produced abiotically.
Exactly.
Correct?
Exactly.
Okay. We have found this on Mars.
Mm-hmm.
We have found this on an exoplanet, K2-18b.
That's correct.
We have also found this on a comet, 67P.
Cherry-Microgrossemenko.
There you
CG.
go. Thank you for saying that. Had a long name. Okay. So,
Wait a minute, you haven't got them all. We found it in the return samples from the asteroid Ryugu. We found dimethyl sulfide in the Orgullian meteorite. So here you've got it in Orgullian, you've got it in 67 PCG, a comet, you've got it in an exoplanet, you've got it on Mars, you got it on asteroids.
the point is, we are so sure
Yeah.
of this substance, of how it is produced,
Yeah.
that we consider this dimethyl sulfide to be what we call a biomarker.
Actually, I would call it not a biomarker. I would call it a biosignature.
Biosignature.
Biosignature I consider to be much stronger than a biomarker.
Biosignature above
A
biomarker.
biomarker is, okay, it could be caused by life. Methane, for example, is a biomarker. But
Okay.
methane is caused by other things.
Okay.
But a biosignature is something that we say, by gosh, this is biology. A diatom is a biosignature. No way are you going to make a diatom by non-biological processes.
Dimethyl sulfide biosignature.
Yes.
Okay,
Yeah.
so we are so sure about it. Okay, so let's talk about this article that you pointed out.
Yeah.
Okay? All right, I'm going to give you a quote here from an article published on science.org.
Yep.
I
Yep.
understand that to be a pretty
Oh, yeah, it's prestigious. Absolutely.
good website.
Yeah, yeah, absolutely.
Science.org.
Peer-reviewed paper, by the way.
Okay, so, quote, after hearing about exoplanet K2-18b, Dr. Nora Hani, a chemist at the University of Bern, wondered whether she could also find the molecule on an unquestionably lifeless body, the comet 67P
Gerasimenko.
okay, which the European Space Agency Rosetta spacecraft chased for 2 years, directly sampling the cloud of dust and gas shed from the icy space rock. Fast forward a little bit. They found it, okay? They found dimethyl sulfide in this cloud of dust trailing this comet. It goes on to say that Dr. Nora Hani, this chemist at University of Bern, says lab experiments will now be needed to pin down exactly how dimethyl sulfide forms in space, because they are under the presumption that this comet is, quote, unquestionably lifeless.
Of course. In fact, she forgot to mention in the paper when they had flown a probe and examined the ice of 67P CG and examined the water on the interior regions and the rocks beneath the surface, and they had found absolutely no microbiology of any kind whatsoever. When they sent that probe and brought back samples, oh, wait a minute, they didn't bring back samples of 67P CG, and in fact, they didn't look for any biology on 67. Oh, they didn't look for anything like that. But Dr. Nora is convinced that the comet has to be lifeless because it is a comet. Well, I suggest that that's not science. That's imagination.
Who came up with
It is junk science, to be very precise. I hate to say that about the individual I know nothing about, but I read her paper, and this is not, the fundamental assumption that she's making as to why you can't call this a biomarker even, is because it's on this comet that we know to be lifeless.
How do we know that?
Nonsense.
How do we know
don't
that?
know that. Nonsense. Nonsense. It's hogwash. That's the whole problem. People are saying things and getting them published in the peer-reviewed literature that don't pass the smell test. They don't pass the smell test. For example, she should say what kind of experiments that she did. If she wants to claim that, she should say, I mixed sulfur and I mixed methane and I put them in a high temperature cooker and I produced dimethyl sulfide, which could have been done in a volcano. Well, the problem is that doesn't happen because you don't have metabolic pathways in volcanoes. You don't have metabolic pathways in cookers. You have metabolic pathways in biology. And these pathways are incredibly complex. One of the pathways is the Krebs cycle, the citric acid cycle. These have one reaction going to another reaction, going to another reaction, and it goes around many, many different activities until you finally get to the end product. And each of those is mediated and controlled by something called DNA. Now, DNA is rarely found in abiotic rocks. In fact, DNA is never found in abiotic rocks unless there has been something in the rock that was biological that died and left its DNA there, or it was stomped on by O.J. Simpson's shoe, one of the others. Sorry about that.
So
couldn't resist.
I think this is awfully bold for either, I don't know if it's her or the person who posted this on science.org, but unquestionably lifeless. If they've done
That's what it said in the paper. Oh, that's what's said in the paper.
Said it's
oh, yes. This is not. Yes.
Qualified how?
Well, I can't answer that.
She doesn't attempt to qualify that at all? She just said
of course
it's lifeless?
not. Of course not. But that's what she said since she was able to find it
Nora,
on
we
the
gotta
comet.
talk.
Yeah, since she said it was found on the comet, that proved that it cannot be considered a biomarker.
What is more likely, that there's microbes on each one of these places, or that there's some mysterious abiotic process that produces this stuff?
Exactly.
I have a link to a NASA webpage, okay? NASA.gov that says, as far as we know, dimethyl sulfide only produced by microbes.
Well, in point of fact, there is a vast body of information about DMS. I have probably 30 papers on my laptop sitting over there on dimethyl sulfide with regard to exactly what kind of organisms produce it. And there is actually, the details of the pathway are laid out and all this sort of thing. So this is not questionable. This is...
How come astrobiologists don't make a bigger deal about this?
Well, the point is, this is, I guess I have to tell you, a lot of the astrobiologists don't know what I just told you. A lot of the astrobiologists who would look at this would not bother to go and say, okay, what do we know about DMS? What kind of scientific literature is there? There's a huge body of literature. And you know why there's a huge body of literature? It turns out that dimethyl sulfide is critical to the sulfur cycle. And it is also one of the gases that is considered a greenhouse gas. So with what happened with regard to global climate change and the climate crisis and all this sort of thing, about a decade and a half, 2 decades ago, a huge number of scientists started looking into the whole subject of dimethyl sulfide. Where does it come from? How does it get produced? And so forth. So the body of knowledge about DMS right now is very, very large, and it is being done by biochemists, by molecular biologists, by microbiologists, by scientists all over the world. And if you told them that you think it is made abiotically, the question they would have is, how did you do it? And if your answer is, well, I think it could be done, then the point is, okay, how could it be done? And if it can be done, why don't you go do it and write a paper about it? If you think it can be done, go do it. So what you're touching on is prejudice in science, bias in science, and one of the things that may be related to this is money. It may be that if you say this kind of thing, you're going to receive a research grant. If you say the wrong kind of thing, you may have difficulty getting a research grant. I mean, quite frankly, I think money plays a big role in all of this, in that you've got to follow the party line.
Okay, all right, hang on a second.
Okay.
This is the last thing I wanted to talk to you about.
This is what?
The last thing I wanted to talk to you about.
All right, okay.
I think you need to go into detail about this.
What?
I think you need to go into detail about this.
Okay.
About the events leading up to your retirement.
Okay, sure. I can tell some details about it.
I mean, this is what you were just getting into here, but I really want you to lean into this.
All right.
Because I think this is important.
Chandra Wickramasinghe.
Because people will say, well, NASA's distancing themselves from
they
Richard
say
Hoover.
that on the website. Yeah.
It's all over the place.
For lack of peer review.
Lack of peer review, to discredit you, to smear you, like whatever.
Okay, to be quite honest, this is hogwash. It is false. And let me tell you why it's false. When I was invited by Chandra to write this paper for the Journal of Cosmology, which he was an editor for, and which had published papers by Nobel Prize winners. So, okay, he wanted me to write a paper about my work on microfossils in meteorites. Well, I started doing that, and I thought, well, it shouldn't just be a hashing of old stuff. I should talk about some other things like water on Europa and Enceladus and so forth. So I should make it a broader paper than what I had originally published. And so it contained a review of a lot of my work that had been conducted between 1996 and 2011, I guess was when it was, as well as other material that was in the paper. I don't know if you've read the paper or not, but it talks about Europa and Enceladus and the like. And I submitted it to the Journal of Cosmology, and Rudy Schild, the astrophysicist at Harvard Smithsonian Astrophysics Observatory, was the editor-in-chief. And when Rudy Schild got the paper, he had had it for a couple of weeks, and then he called me on the phone and he said, "Am I reading this paper right? Are you saying that these fossils were in the meteorites when they entered the Earth's atmosphere?" And I said, "Yes." He said, "You're saying this is extraterrestrial life?" And I said, "Yes." "My God, this is important." I said, I've been reporting on this for years. I said, "I don't know whether it's important or not, but these are my findings, and so that's why I wrote it, because that's what I found." And so then he said that what they wanted to do was and Chandra will confirm all this for you as well, and Rudy Schild will also. He said what they wanted to do is they wanted to send this out to 5 reviewers, not 3, but 5 referees. 5 referees, and they also wanted to send it to 100 scientists for commentary, and he wanted to know if I would recommend 10 scientists that were capable of reading and understanding this work that might be willing to give a comment about it. Well, I told him yes. I said, but these are people that I know and people that I've worked with. He said, that's okay. So I gave him names like Alexei Rozanov and people like John Carriage, who was not a very close friend, people like Elena Pikuta, who I'd worked with and knew the work intimately. So I came up with 10 names, but he was coming up with 90 other names, like Bill Schopp and other people. So, I wasn't tilting the scales as it was. But before that happened, I told Rudy, I said, how in the world am I going to respond to 100 referees? No. They're not going to be referees. We've got the referees assigned. These are going to be asked to give comments, positive or negative, about their assessment of this work. Okay, no problem. And they were going to publish these commentaries simultaneously with the publication of the paper. Fine with me. That sounds great. I'd love to hear from some of these other people. So I'm working one day at the science fair, and I was judging a science fair, and I got a phone call, and I was told that they were going to publish the paper that night, and they wanted to give me a heads up. Well, that was the first I had heard that it had been approved for publication. In fact, I would have sworn it could not have been, because I had received referees' comments from 3 of the 5 reviewers. 2 of them had never returned, not said anything, and 2 of the 3 had recommended it be published without change. And one of the guys was cantankerous and said, page so-and-so doesn't make any sense at all. And I thought, what's wrong with this guy? And so I went and looked at the page he had called out, and I thought, oh my God, it doesn't make any sense, because I had written it in Microsoft Word, and on one page I had somehow managed to highlight a big chunk of text and hit a period, and poof, the 2 or 3 paragraphs vaporized and came a period in the middle of a sentence, and so you had a completely disjoint thought, which told me that the other 2 reviewers hadn't really read it extremely closely, but this guy did. And, or woman, I don't know who it was really, but whoever it was that reviewed it. And so when he told me that it was going to be published that evening, I said, well, you can't do that. He said, why not? I said, because it's got some errors I need to correct. And I was shocked too that they were saying they were going to press. And that's when he told me that it had leaked. And what had happened, well, actually, the next thing that happened while I'm judging this science fair, I got a phone call from a guy by the name of Bill Hemmer. Now, Bill Hemmer at the time was not a very well-known journalist working for a television program called Fox News. And Bill Hemmer wanted to talk to me about my paper. And I said, which paper? He said, the Journal of Cosmology paper. I said, well, that paper's under embargo and under peer review. I can't talk to you about it. He said, well, he said, my understanding is it's being released from peer review, from embargo, and we're going to do a story about it. I said, a story about it? And he said, yes. And I said, well, look, I'm busy. I'm judging a science fair, and I'm right in the middle of some things. Could you call me back in about an hour? Well, I was telling the truth. I was judging a science fair. I was fibbing. I was perfectly capable of talking to him about whatever question he wanted to ask, but I didn't want to. So I got off the phone and I called Janet Anderson at Marshall Public Affairs office. And I said, I just got a phone call from this guy from Fox News wanting to talk about this paper. Is it okay for me to talk about it? You've talked to the press before. And she said, we don't have any problem with that. And she said, I'm sorry, I gave him your phone number. I knew you were judging a science fair, but he said it was important and wanted to talk to you about it right away. And I gave him your cell number. Is that okay? I said, yeah, no problem. As long as it's okay with Marshall, I don't have any problem talking to him. So then I called Rudy. And I said, this guy from Fox News wants to talk to me about it. And he said, yeah. He said, they're going to publish a story about it tonight. And I said, how? And he said, one of the people we sent the manuscript to do the commentary apparently leaked it to Fox News. So they had the whole manuscript, and they were going to do a story about it that night. Well, I'm trying to decide, what am I going to do? So I told Rudy that I needed time to fix some of these problems. I explained the problem that I had discovered. And he said, well, we can hold off until about 7 o'clock because apparently the program was going on at 8 or something like that. Anyhow, I told him, well, if I left the science fair right then, I could get home and correct it. Just about this time, the phone rang, and I had clearance to talk with Bill Hemmer, and he wanted to know what are cyanobacteria. I'm thinking, that's 8th grade biology is what that is. That's what cyanobacteria are. You learn about them in 8th grade biology, but I wasn't snippy and didn't say naughty things like that. I explained that cyanobacteria were called the blue-green algae, that they were photosynthetic bacteria that were abundant and had been abundant on Earth for about 3.2 billion years. And then he said, you're saying you found fossils of these in the meteorite? And I said, yes, that's correct. And he said, so you're saying they're extraterrestrial? And I said, yes, that's what I'm saying. And he said, okay, thank you. And that was basically the end of our conversation. You know, he basically wanted to know if I existed and if I was nutty enough to say what I had been nutty enough to say. So I went home and made the corrections and sent them off to Rudy Schilt so that the thing they put online would be suitable and not have too many errors in it, although I had corrected only the ones that I had been able to see from the from the referee that really read the paper carefully. Well, there were a couple of others that caught some typos and so forth. So anyhow, it went in to be published, and they came out with the story on Fox News, and my wife was in the hospital with cancer, and I wound up spending the entire weekend after I got this sent back to the journal with her in the hospital, and didn't even come to work on Monday. And when I got to work on Tuesday, there had been an enormous firestorm. I was told by Chandra and by Rudy that the story had gone viral. I was told that their website had crashed with people trying to download it, and I think in the first week or two, it was something like 1 or 2 million attempts to download the paper. There were stories written about it all over the world. I've found stories in just about every language imaginable about this. And I get in on Tuesday morning, and my boss is telling me that NASA's furious that they didn't know anything about it, and there had just been this Felicia Wolf-Simon paper about arsenic that had caused NASA embarrassment, and the David McKay paper had caused NASA embarrassment because there weren't really any microfossils in the Mars meteorite, and Felicia Wolf-Simon's paper about arsenic replacing phosphorus in DNA was not right, and NASA had never heard of this. And I'm sitting here saying, wait. NASA's heard of this because I've been publishing papers about it and chairing conferences about it since 1997. But I mean, there may be some people at headquarters that have had their head in the sand and don't know anything about it. And then Dennis told me that they were upset too because the paper hadn't been subjected to peer review. And I explained to him, well, there had been 3 referees that had responded, 2 hadn't yet, but I responded to all the referees' comments. And then he said the problem too was it was never cleared. And I said, never cleared? I said, no, I cleared it. That's what you have to do with these papers. Although what we worked is we would always submit our paper for clearance, and when it got cleared by the center director, we could then send it to the journal and then be assured that it was going to be okay. So because we knew those people would take a couple of months, and we waited a couple of months, then we would finally send it to the journal. So it was our practice to send the paper after we got clearance from Ernst Stuhlinger and from the center director and the various laboratory directors, if any of them were involved, including my director at SSL. And so anyhow, I went back up to my office thinking, did I mess up? Did I really not clear this paper? And went to my desk, which was always piled high with papers. That was my filing system. And I started doing an archaeological dig, and about a third of the way down in the stack, I found the proper clearance form. And I pulled it out, went to the Xerox machine, made a couple of Xeroxes, came back, put the original in my filing cabinet. And then I went down and I went in to see Dennis Gallagher, who's still at NASA and my boss. I said, Dennis, you told me my paper hadn't been cleared. Yeah, he said, they're very upset about that. It never was cleared. I said, Dennis, do you recognize the signature on this piece of paper? There was a signature of Dennis Gallagher. I said, did you fail to keep a copy of this clearance form when it was cleared and was returned here? I said, it was cleared. I don't care if they say it wasn't cleared, if they say it wasn't peer-reviewed. That was not correct. And they had actually gotten one of the people there.
Do you still have that paper?
Oh, yeah, of course I do.
Can you send me a copy?
Well, I mean, the clearance form, I doubt it. I'm sure I have it. But now that's the first part of the question. The second part of the question is, could I find it within a reasonable period of time? And the answer is, no way. It's probably in a box.
We got to do another archaeological dig.
Yeah, it's probably in a box downstairs in my garage somewhere, because now then it's not important.
We'll do next time.
Yeah.
Okay. Go ahead. So you got it cleared.
So it had been cleared. And it had been peer-reviewed, and they said they didn't know anything about it. Well, it had gone through all the proper offices at NASA headquarters. So the problem was their people were saying things that quite simply were not true. Now, why they were doing this is strange, but it may have to do with money, because if you think about it, if there is evidence for the existence of extraterrestrial life, can you keep going back to the watering fountain and saying we need X billion dollars to support a program to look for evidence of extraterrestrial life? And in fact, for a long time, they've not been saying they've been looking for life. They've been saying they've been looking for water on Mars. And, follow the water was the big theme for years. Since Viking, which discovered evidence for life on Mars, there have been exactly 0 life detection experiments flown by NASA. None. Now, wouldn't you think that they would fly? There are many experiments that can be flown. And in fact, the first astrobiology briefing that I attended, we were told in no uncertain terms, if you submit a life detection experiment proposal, it will not be accepted. Gil Levin and I submitted the TWEAL proposal, and it went to NASA headquarters, and it was returned to him unopened. So NASA was not the least bit interested in funding a life detection experiment.
Okay, so you went back through your records, you found the clearance, you did everything you were supposed to do.
Yeah.
Okay, then you get invited to the Gordon Conference.
Yeah.
In the midst of all this.
A few weeks after.
So what the heck is the Gordon Conference?
Oh, well, the Gordon Conferences are very prestigious. This was a Gordon Conference on the origin of life in Galveston. The chair was none other than Steve Benner, who you know. Steve called me to invite me to give a presentation at the Gordon Conference in January of 2012. And,
nice of him.
Huh?
That was nice of him.
It was nice of him.
He's a heck of a guy.
He's a brilliant guy and a very nice guy, and he made the invitation, and I told him I would be delighted to, and he told me he wanted me to talk about my paper, essentially, Microfossils and Meteorites. So I accepted, and then realized, okay, I got to get this thing cleared. So I was in the process of starting to put together the paperwork to get a presentation. Now, Gordon conferences are supposed to be discreet. You're supposed to be able to talk about new ideas that have not been published. You're supposed to be able to talk about things that people are not going to talk about outside. So you can discuss anything you want to. And even if you think it may be a little bit on the edge side or crazy side, you're welcome to put it out there and have comments back from other scientists who give you their interaction and their feelings with regard to what you're doing. So it's a very special kind of meeting, invitation only. Well, I hear footsteps out in the hall, and I walk out in the hall, and there was my boss, Dennis Gallagher. And I said, Dennis, I wanted to put in travel orders to go to Galveston in January of 2012. And Dennis said, to Galveston, he says, what do you want to do there? I said, I wanted to give a presentation at the Gordon Conference. Well, you can't just go to a Gordon Conference. And I said, why not? You can't just go to a Gordon Conference. Those things you have to be invited to. So you can't go to a Gordon Conference and give talk. I said, but Dennis, I was invited. When? Oh, 15, 20 minutes ago. You were invited to the Gordon Conference. What Gordon Conference? The Gordon Conference on the origin of life. What do they want you to talk about? Microfossils and meteorites. Oh, good Lord. You know all the flap that caused. Are you sure you were invited? I said, yeah, I'm pretty sure. Well, I've never been invited to a Gordon Conference. I said, I didn't know that. What? Well, money's awful tight, I'm not sure we'll be able to handle that. I said, look, Dennis, I'm not asking for 3 months in North Siberia. I'm asking for 3 or 4 days maximum in Galveston. I said, if NASA can't find the money for a plane ticket, I can drive my own car. Galveston's not that far. Well, you got to make sure you get that cleared. I said, yeah, I understand. I'm working on that right now. because this was, I don't know, May or June, presentation in January. Yeah. So I filled out the paperwork and travel order requests and all this sort of thing, sent it over to Janet Anderson on the proper forms with an abstract and a bio, and go back to work on doing other things. And some time goes by, and sometime in July, I think it was, June or July or August, I got a call from Steve Benner wanting to know if I'm going to be able to come. And I told him, yes, I was planning to. I said they had said something about there being problems with funding. He said, that's not a problem. He said, if you can come, we'll pay your travel. He said, if you can't get travel from NASA, we'll pay your travel and lodging. So I said, okay, that's wonderful. Thank you. And then he said, when can you send me your abstract and title? See, I hadn't even given a title yet, and bio. And I said, well, let me find out where the clearance is, and I'll let you know. Well, I called Janet Anderson, and she said, yeah, it's been a while. Let me call headquarters and see what's going on with the paper. And I said, well, it's just a presentation. It isn't a published paper, but I really need to get it cleared because they're wanting the title and abstract and bio. Okay, I'll look into it. So I think it was the next day or 2 days later, I get a call from Steve Benner, and he said, something strange is going on with your Gordon Conference presentation. And I said, what do you mean? And he said, we got some phone calls this morning about your presentation. So what do they want to know about it? They wanted to know if we would disinvite you to the Gordon Conference. I said, they what? He said, they wanted to know if we would rescind the invitation. I said, what did you tell them? I told them it was my decision. We had no plans whatsoever to rescind the invitation. And I said, great. He says, do you think you'll be able to come? I said, yeah, I'll be there. He said, no problem. So he said, well, when can you get me your title and abstract? I said, 5 or 10 minutes. As soon as we hang up the call, you'll have them. So I hung up the phone and went to my file in my computer and sent him the title, abstract, and bio. I walked down and went to Dennis's office and said, Dennis, regarding the Gordon Conference, I wanted to withdraw my request for travel. Oh, great, you decided not to go. Oh, no, I'm going. You can't do that. Your paper's not been cleared. How do you know that? Well, it hasn't, has it? No, I said, as a matter of fact, it hasn't. But never mind that. I'm going anyhow. Well, you can't do that. If your paper hasn't been cleared, you can't do that. I said, well, actually, Dennis, I can. Because I'm going to retire from NASA. This wasn't the agency that I hired to work for. This isn't behaving like the agency that I expected it to be. And come January the 1st, 2012, I will no longer be an employee of the National Aeronautics and Space Administration. Turned around and walked out of his office, went upstairs and filled out my retirement papers, and came back and presented them to him because I had enough years I could retire for any reason I chose, and it was my decision, not theirs, whether I wanted to stay or not. So I turned in my retirement requests and went back to doing other things, and went ahead and prepared my presentation. And come the 1st of January, 31st of December, technically, I was retired from NASA. I had already processed out and everything. And then on the 4th, I think it was, I went to Galveston in my own car. And, well, actually, no, I didn't. I flew from Huntsville to Houston and then rented a car and drove to Galveston and gave the presentation at the Gordon Conference. And what was interesting is the chair of this conference was a famous meteoriticist by the name of Sandra Pizzarello, the chair of the session I was in. The same meteoriticist that had studied all sorts of organics and meteorites, and that had sat there when I gave a presentation with Paul Davies in his meeting and had not looked at any of it because she'd been reading her email the whole time. So there she is now, chair of the session, standing there. I'm giving a talk showing the slides. And so when it finished, Steve Benner said, he says these are microfossils in the meteorites. I would like to know if anybody can explain how you could get microbial remains, modern biological contaminants, into a meteorite without also introducing all 20 proteinogenic amino acids and all 5 nucleobases. And nobody made a suggestion. Nobody. And Chandra did not make a comment. She did not ask a question. She didn't say a single word. Nothing. So the point is, a couple of days later, I went back to Huntsville, and I then continued to work on microfossils in meteorites. But that was so fortunate because I was able to spend the entire year with Miriam and go places with her and do things and see things. And that was the last year that I had with her. So it turns out that my retirement from NASA came at a very fortuitous time. And even though I retired from NASA, I didn't shut up. Nobody told me that I couldn't say whatever I wanted to say. And as you can tell right now, I'm perfectly willing to say exactly what I think and remember things exactly as I remember them. Now, it may be that there will be people that will disagree with that, but I can absolutely prove that that was precisely when I retired, and that was the reason I retired. And I actually wound up, after retirement, Dr. Pakuta and I went to Athens State University. They closed down the entire astrobiology program at NASA Marshall Space Flight Center. So no one is doing astrobiology at NASA Marshall. No one did anything in astrobiology after we left. And all of the equipment that we had got accessed and was transferred to Athens State University, and we established the Astrobiology Laboratory at Athens State University and worked there for 2 or 3 years and discovered several new species and genera of bacteria while doing the work at Athens State. Miriam and I, we loved the same things. She was an unbelievable individual. She loved to go out on a crisp autumn morning with our Brittany Spaniel and put on boots and slog through the Alabama mud and clay as we walked behind the dog waiting for our dog Cher, our dog Bonnie, which were Brittany's at the time, and waiting for them to come on point on a covey of quail. And then when they would lock up on point, I would come in and flush the quail and shoot. And if I hit a quail and it fell, the dog would stay absolutely rock steady to wing shot and fall. And then when Miriam would give the command, it would run out, fetch the bird, and bring it back to hand. And so she trained these kind of hunting dogs, and she loved firearms. She loved. We went to Austria during that year, and we went to Furlock, and we saw the most incredible engravings being done on shotguns that were amazing. A friend of mine in St. Louis owns a gun that was actually manufactured for the Tsar of all the Russias. And this is an incredible piece of art and magnificent weaponry. But that's what she liked to do. She liked to go hunting. And we always, when we would shoot birds, we always brought them home, and she always cleaned them properly. Well, I usually cleaned them, but then she always cooked them with dove breasts wrapped in bacon, and it was delicious, absolutely delicious. So we loved scuba diving. In fact, on one occasion, we were scuba diving on the Great Barrier Reef, and we came across a clam about 8 feet in diameter, and Miriam went over and motioned me, and I came to the clam, and before she left, she reached in to pet the clam, and these giant shells started closing just like that. Of course, it couldn't close fast because it was pushing against tons and tons of water. So I decided, okay. So I reached in, gave it a couple of pats, and skedaddled. We went a distance away and sat and stood there in the water and watched the clam close. We had fun with all kinds of things like that.
Could you leave us with some parting words in French?
Il faut se nommer lugubre pendant que je méditais faible et fatigué. Soudain, il se fit un tapotement comme de quelqu'un frappant doucement à la porte de ma chambre. Ce n'est que cela, et rien de plus.
This is the continuing series of Blue Planet Red, an award-winning documentary film on the history, evidence for life, and catastrophes that contributed to the death of Mars. The documentary includes interviews with NASA's lead astrobiologist, university professors, aerospace industry scientists, and independent researchers. If Mars was like Earth in the distant past, could there still be life there now? What happened to it? And what turned a blue planet red?